we're gonna go into recording first and then our poster session, right? Sorry, first spotlights, then poster session.
Okay, hi, thank you. I'm Moritz from the Intuitive Robots Lab, and I'm excited to present our work on scaling robot policy learning via zero-shot labeling with foundation models, which was led by my student, Niels. Language condition imitation learning has become one of the most versatile ways to train agents that can actually solve a range of tasks in the real world. The general process to train these agents is quite simple. First, we need a large-scale data set, and then we require either a set of poor undergrad students or some other crowdsourced humans that then label all of these trajectories so we can get a fully annotated data set. Finally, we can then train a policy of our choice to then hopefully perform versatile tasks in the real world. If we look at this general framework, we have several advantages. Language is a really intuitive interface for humans to communicate, and it also offers great generalization thanks to the good language models available. However, this general process of manually labeling all of the data sets is not really scalable in our age of trying to come up with larger data sets that are hopefully fully annotated. So given this expensive framework, we wanted to find a way where we can automatically perform hindsight relabeling without any human intervention or help. And to do so, we introduced Lupus, the first framework that can automatically label a data set from a single static camera without depth information and also segment long horizon demonstrations effectively, which allows us to train language condition policies in a zero-shot manner. Lupus consists of 3 stages. First, we require models to actually detect what objects are in the scene and how we could manipulate them. Therefore, we use VLMs to generate a large list of all objects by looking at multiple images from our video and then generating a possible target list using large language models. Next, we label all changes and movements that are happening in the scene with an ensemble of specialists such as flow estimation models, depth tracking models, and object detection, all of the movements and changes of our robot and objects in the scene. Finally, we can use these object-centric changes to identify the key states in our long horizon video, which we can use to generate object key scores together with an estimate of how confident we are. Finally, we generate a list with all of the changes that happened and ask a large language model to accurately label what kind of task was solved in this short horizon segment. We tested our framework on several challenging real robot environments, such as a kitchen dataset in our own lab and the famous MOMA.v2 dataset consisting of over 60K trajectories. In our first experiment to see if we can accurately segment long horizon videos, we are able to show that we outperform all other zero-shot key state segmentation methods, such as UVD, in both bridge and kitchen. Further, our framework significantly surpasses state-of-the-art VLMs and other models such as XClip on the actual grounding, so the task generation in our own kitchen and on bridge as well. Finally, we then trained an actual language condition policy in our kitchen based on synthetic data only, and we're able to show that this is competitive with a fully annotated data set. We hope to further scale this up and are right now trying to label full bridge and the OXE dataset to further enable to language policy to scale up. Thank you.
questions? Okay. So I think we'll just do all 3 spotlights, and then we can take 1 or 2 questions for all the papers afterwards. Unfortunately, the next authors are not able to present here in person, so we will play a video for them. Thank you. Thank you. Thank you.
Today, I'd like to present our work, MobileAfford. Mobile robotic manipulation.
Mobile robotic
Different.
mobile robotic
Different.
mobile robotic different mobile robotic different mobile
I'd like to present our work, However, in recent mobile manipulator. Robots are capable of navigating. Strategy. We evaluated our proposed method on the We evaluated our proposed method on the We evaluated our proposed method on 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 manipulation. 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 Manipulation.
Unfortunately, we are going to have to skip this video. We are going to have to skip this video. No.
I think now that I unplugged this.
Okay, perfect. All right, let's go with the next one.
Ja, ich weiß es nicht. Ja, perfect. Do you have some? Yeah.
This one. Am I screen sharing? Oh. What is this?
It's just, it's fine.
But it's not a.
I think the last one took a second.
Okay. Oh, okay.
You can see the slides on Zoom, but where did she?
Oh, yeah. Is it my laptop?
It could be that it's your laptop. It's actually gone.
Can we try to plugging that laptop in?
Because you have it on Zoom, yes. Can do that.
Because it's weird that it's not showing absolutely anything.
Okay.
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 That works.
You have to
Okay.
Right,
move the
control
slides
this,
here,
right?
and then
All right.
I guess this is full screen as it goes.
Great.
Hello. Hi, I'm Sneha. I'm presenting What Do We Learn from a Large-Scale Study of Pre-trained Visual Representations in Sim and Real Environments. So recently, there's been a bunch of works that came out with PVRs for robotic control. And we wanted to ask the question, is the performance of PVRs in simulation predictive of their performance in the real world? And we do this by looking at sim predictivity. So what we did was we trained a set of policies using simulation data, and then we trained a set of policies using real data, and we look at their correlation, the Pearson correlation coefficient between the performance of these two policies when they're evaluated in their respective sim and real environments. We call this sim predictivity, or SRCC, for sim versus real correlation coefficient. So we compare 5 different PVRs on mobile manipulation and navigation scenes with 3 different embodiments and 5 different tasks, and then we evaluate them both in sim and on the real robot. The first question we ask is, how do PVRs perform across different robotics tasks? We wanted to see if there was one PVR that dominated across all of these tasks for Cortex Bench, as well as for our 5 tasks. We didn't see any clear PVR that dominated, but we did see that on average, VC Large performed best on Cortex Bench, and then VC1 Base performed best for our set of tasks. We wanted to see if the performance on the simulated environments could predict the performance on the real robots. With Cortex Bench, we didn't see a positive SRCC, but with our setup, we saw a positive correlation when you match the setup so that we had the same number of demonstrations used in sim and on real. And then we wanted to then take a look at whether these simulated policies could be transferred to the real robot directly. We did see a drop in performance, if you look at the red, for all of the tasks, except for image nav, which was trained using reinforcement learning, and it was trained directly in simulation, transferred to real. So there was no corresponding set of sim policies and real policies. Lastly, we wanted to take a look at how we could do downstream training and improve our performance. And we found that fine-tuning using a base model and not using augmentations produced the best SRCC values. And on average, for both VC1 and VC1 large, base and large, fine-tuning and having augmentations yielded the best performance. And overall, the models VC1 base fine-tuned and with augmentations on average yields the best performance. That's it.
All right, we're going to take a couple of questions for any of the 2 speakers, of the spotlight speakers, and then we will go into the poster session. Questions for our first speaker or our second speaker? All right. Yeah, go ahead.
Hi, my question is for the first speaker regarding lupus. So in the last step of lupus, you said that you query a large language model to get the final grounding of what happened. So my question is that how do you evaluate the output of language model, whether it's accurate or inaccurate? Do you?
Sorry, could you repeat the last sentence?
How do you evaluate the output of the large language model? Is it done through humans or is it?
So to test like how good it is, we used human labels and then compared the overall labels.
Okay.
Actually, that's a challenging problem
Yeah.
because there's no real ground truth.
Exactly.
For example, on Bridge, we noticed that a lot of labels that were crowdsourced are not really precise. So we thought about like we actually used large language model and clip scores to get like different values to better evaluate it. But it's not so easy given the ambiguities in the general language.
Okay, yeah, thank you.
My question is also for the first speaker. Sorry to make you go back and forth. So I was curious with your action classifier, how do you think that could be applied to videos of like human actions? And do you think those could be used to get like a bigger source of data than just using robot demonstrations?
So labeling human data also works. If right now the main limitation is that our one camera needs to be static. In general, actually labeling human action is easier because all these pre-trained models, since we don't use any training, they are not usually trained on robotics data. So for them, detecting like human movements is actually a lot more easier than detecting different robot grippers. So in general, it should work as well.
Thank you.
All right, so we're gonna go into the poster session and coffee break, and we will be back at 10:30 for our next invited talk.
Maybe just one word to add. As we have a best poster award, we will also have a vote for the best poster. Oh, it's already up. So if you go to this QR code, you will be able to vote for the posters of the morning and afternoon session. Yeah, thank you a lot.
We need your vote.
All right, hi everyone. So we will continue with the next presentation. Yeah, if you could just please keep the volume down at the posters a bit. And next we have Mehmet Dogar, professor at the University of Leeds, doing a lot of research in physics-based models and collaborative task execution. So we're really excited to have him here. And yeah, please.
Is it now? Yes. Okay, good. So I should say, hello, today I'd like to present. Hello, today I'd like to present. Hello. Okay, so we do a lot of work in manipulation, and particularly in cluttered environment and using physics-based models, and today I would like to speak a little bit about that. When I say manipulation in clutter with physics, what I mean is scenarios like this, where you have a robot trying to reach into a cluttered space, for example, a bin or a shelf or a drawer in your home, a mobile manipulation system driving around and reaching for objects in those spaces. So here, for example, there are multiple objects, some of them rigid, some of them deformable, like the teddy bear there, and the robot's task is to reach for that object with the star on it. And to do that, the robot would need to reach in there, predict how these objects will be moving and squeezing in the case of the teddy bear there, right? and then to create the space to reach for the target object and go pick it up. And this is what we call physics-based picking, interacting with multiple objects simultaneously while predicting the physical interactions consequences there. And you can also think of the inverse problem where, that is the packing problem, where the robot already has an object in its hand and it wants to pack it tightly, so it needs to go there, again, predict how those objects will move to nudge them out of the way to create the space and insert it in. So this is kind of the vision that motivates the research that we are doing, and we are looking at the different components, planning, perception, control, that can go into such a system. And what I will do today is first I will show a couple of videos from a previous work just to give an idea about what kind of problems and systems we are interested in. I won't go into details of those, then I will go into the details of some most recent work, but just 2 videos first. This is just an example system that we had built that search for objects in a shelf. So here in this case, let me pause this for a second. So in this case, did it pause? No, it didn't pause. Oh, I can't pause it. Anyways, so in this case, the robot is searching for an object. The camera is on the hand. That is what you're seeing, and that is what the robot is using. There are AR tags on the objects, as you can see. This system is using physics-based planning and learning in a combined way. What I mean is there is actually a receding horizon planner here that is running physics-based rollouts, which you kind of can see on the top right there. But the main challenge in physics-based planning is really the computational cost of making these physics-based predictions. And therefore, that is why it is a receding horizon planner. So the horizon that the planner is searching for is actually quite short. And now what happens is that also in these high-dimensional spaces, it is quite difficult to estimate the value of those states that you reach at the end of the short horizon, right? So that is, for that we are using learning. So let me play this again if it works. Yeah. Therefore what happens is that at the end of those rollouts in the physics-based scene, what we have is a neural network predicting how good that state might be, and which is driving the planner. On top of that, the learning system here also predicts where the hidden object may be. So the green object there is the target object that we provide to the system, and so the planner and the learning system are working hand in hand here to reach for the target object. So, but yeah, so this is one example of a planning / control system that we have, and an example of the kind of problems we have. Now, having said that and having talked about planning and control a lot, here, as you can see, we have these AR tags on the objects to detect them. And that is very challenging, because while you're doing planning and control in such scenes, actually the perception problem can also be quite difficult. And you might actually not only need physics-based predictions for planning and control, but you can actually make use of physics-based predictions for perception as well. That is something we are also interested in. The reason is that normally the practice in our community is just to use a camera to detect objects, right? Now, that most of the time works, but actually in these cluttered spaces, if you have your hand in front of objects, or when you're pushing, one object can block the view to the other object, and then it is very easy to lose track of these objects. The thing is, though, actually, if you know how the physics should move objects, as you are pushing an object, even if it is blocking another object that is pushing, if you know how those two objects should interact physically, you can estimate something about how those hidden objects are moving, which is something that we are also interested in. This is a perception system that is using vision, but also physics-based prediction. So what you will see is that even when some of the objects are really occluded, especially at the end of this video, you will see that that can is almost completely occluded. We are still able to predict its motion and where it is. Because we're using vision, but also we are using how these objects physically are interacting with each other. And that gives us the cue about how the hidden objects might be moving and where they are while we are interacting in these cluttered spaces. Right? So, so this is just to make the point that this integration between perception and planning and control, as the organizers of the workshop also emphasized today, actually that the physics reasoning is definitely, I think, one of the things that ties them together as well. Okay, so we are interested in planning and control and perception, but today I will actually mostly focus on our planning and control work, and I will now mostly talk about two recent work we did in this space. And those are to address two big problems that we have in building these kind of planning and control algorithms. One is that these kind of systems that we are acting in is high dimensional. So because when you have a planning problem in these kind of spaces, you don't only have the robot's degrees of freedom, you also have the object's degrees of freedom. If they are rigid objects, that's fine, you just need to pose. But if you have deformable objects like the teddy bear there, then of course they can be a much higher dimensional, but in total you have a very high dimensional system. And the second problem is that these physics-based predictions are very expensive in such systems, and that is one of the main things that really obstructs the progress in this area in terms of using, for example, MPC methods, which can quickly return controls to execute in such systems. And so some of the most recent work that we are doing tries to address this problem. How can we actually deal with this? The fact that these are high dimensional and computationally expensive in terms of the physics rollout systems. And two solutions that we have recently explored are, first, trying to think of approximating the dynamics, approximating the physics, to reduce this cost of physics predictions. And the second is reducing the dimensionality of these systems. And I will talk a little bit about those today. Now, in terms of approximating the dynamics, our intuition here is that when we have physics models of an interaction between the robot and the objects, and the objects and the objects, well, we don't always need highly accurate predictions, right? So a good example of this is these videos, which is from a paper that we published a while ago, but basically here in this work, what we were exploring was, in given two different scenarios, you might actually need different accuracy for the physics model. So for example, so the task in these two cases is the same. You are trying to push the object to the green region without making it fall off the surface it's on. And in this case, it is the same planar controller that is working in these spaces. But what the planner is doing is trying to adjust the accuracy of the physics predictions to the level that it is required by the task. What I mean is, on the left, you actually need quite highly accurate physics predictions for this to work, because you don't want the object to drop if it moves in an unpredicted way. And you also have a very small goal region, so you have to shoot for it in an accurate way. So the robot has to move quite slowly, and the planner also has to move planner has to work quite slowly because it requires high accuracy predictions. But there are also cases where we don't. This is an example of the case where the object, it's very difficult for it to fall off that big table it's on, and the planner is aware of that, and the goal region is quite large. The planner is aware of that. So the accuracy of the predictions can be quite low, and then everything can speed up starkly. So now, we have been exploring this idea quite a lot, and most recently we have been looking at using this idea in trajectory optimization. So trajectory optimization is the method where, especially contact-based trajectory optimization, where you are using gradients of the dynamics. So that is, you have your physics model and you have to extract the gradients from it. To give a very brief introduction to it, when you have a trajectory, what you have is states until a certain horizon, and the controls use until that horizon. And when you do gradient-based trajectory optimization, what you use is something called dynamics gradients, basically. So what this is at each time step here, you need to build a matrix like this, basically, as you're doing this trajectory optimization. And this matrix is actually easy to understand in the sense that, so this is each element here. Let's say, that delta x1 to delta u1. So let's say x1 is one of the state variables. So it might be the position of x position of one of the objects, right? It is one of the variables in your state. And then u is one of the controls. Let's say it is, your torque at a certain joint, right? And that expression, what that says is that, okay, as I change the amount of torque I'm applying at this joint by a very small amount, how does that x position of that object change in the environment? So basically, this matrix is just trying to express how all the different state variables change as each control changes. Now, you can build this matrix if you have analytical expressions of your dynamics, but in these cluttered high-dimensional spaces, we actually almost never have analytical expressions. So you can't just take the derivative of an analytical expression. What happens most often in trajectory optimization with contact is we use a method called finite differencing. So finite differencing is when you have your simulator, so you don't have the analytic expression, but you have your simulator, what you do is you put all the objects at where they are, and then, so if the question is how the x position of this object changes as you change this control, what you do is you change this control a little and look at how the x position of this changes. You change this torque a little in the other direction, and then you look at how the position of this changes, and then that is how you try to estimate the derivatives, okay? Now, but each of these, this is called finite differencing, and each of these requires you to run the simulator, okay? And if you actually, when we were looking at these trajectory optimization methods, what we realized is that this is the bottleneck of these methods. So what I mean is that, so let's say, and these optimization methods can be used for manipulation or for locomotion as well. So here, for example, this is from one of such trajectory optimization methods called ILQR, iterative linear quadratic regulator. And here, this is an example from a Walker it's optimizing. And you don't have to look at everything here. So basically, just let's look at this blue bar here. Just focus on that, please. So the horizontal axis here, the 60 there is the horizon of the trajectory optimizer. Okay, so don't worry about that as well. But basically, and on the horizontal axis, on the vertical axis, you have the iteration time, how long each iteration of ILQR takes. And so this blue, this blue bar, what it says is that it takes about 12.5 milliseconds each iteration, right? So now, but what is the dark shade of color shows is the share of computing the derivatives when you are doing ILQR. So, and then in ILQR you have a backwards pass and a forwards pass. That is what the BP and FP are. But basically, what we are trying to show here is that all these dark colored bars, which are the times you spend on computing the dynamics derivatives, completely dominate the planning time. So, and that is the physics simulation. That is where you are doing this finite differencing. That's like you're rolling out your physics simulator forward to estimate the physics. So that is how you compute. So the question then we asked was, okay, going back to what I said about, okay, do we always need high accuracy dynamics? Our question was, okay, if we can actually reduce this dark bar, the time we spend on computing dynamics derivatives, then we can really speed up these trajectory optimizers. So what we have been looking at was, okay, can we actually avoid computing this matrix, the dynamics gradients? Can we avoid computing it at every time step and only compute it at some key points where we need high accuracy and then approximate it in between? And that is the method that we try to implement. So for example, this may be the values that you get for only one of the elements there. That is over time. So this is a trajectory of horizon 3000. And the yellow dots are where we actually compute the value, so where we pay the price of physics simulations, and in between we just approximate. So that we can actually reduce from, and the underlying blue dots are when we compute the dynamics at every point. That is the underlying thing that we don't want to do. And what we were able to show that actually we can do this. We can use approximations for most of the parts of the task. And you might be asking, okay, how do you decide on where to compute these yellow dots, the dynamics, and where to avoid it? We looked at different methods. You can think of really different methods. One method that really worked well for us was looking at the jerk of the system. So basically, we used jerk, which was related to contact, as key points where the dynamics changes a lot. So we mainly computed these dynamics only at those key points that try to approximate in between. And then we actually recently applied this method to not only ILQR, but other planning methods. And originally we had implemented this using the Mujoko simulator, but recently with the help of ICRA from Toyota Research, we also implemented this on Drake as well. So if you're using Mujoko or Drake and using trajectory optimization methods, then you are using gradient-based trajectory optimization. Actually, like, please feel free to get in contact with us because we have APIs for if you are computing dynamics derivatives at each time step, you can actually avoid it. We can quickly test if your system can make do with much fewer dynamics evaluations, so which is what we did in our collaboration. But so here we applied it to all these problems, and it is not, the method is not specific to ILQR. It can be applied for any method that uses dynamics gradients. And what we've seen is that depending on the task and the robot and the simulator, the speed up that you get can change, but you do get a speed up. So for example, on the top right, that was a single object pushing task within Mujoko, and then we got a very small amount of speed ups, but for ball rolling tasks or for clutter manipulation tasks on the middle there, we got really big speed ups. So it can change depending on the task. As I mentioned, the accuracy you need changes according to the task, but you do get speed ups from that. Okay, so very quickly, then I also want to talk about dimensionality reduction. So, and the idea here is similar. Again, we want to make the physics cheaper. And in the first case, we were approximating dynamics. Here, we are asking the question if we can actually go from a high dimensional representation to a low dimensional representation. And the thing, again, this is also task dependent, right? So one example that I always give is if you are manipulating a cloth, let's say a t-shirt, if you are going to fold it neatly, the model that you want to use of the t-shirt probably needs to be high dimensional. You need to represent many points on this t-shirt. But if you are just throwing it into the laundry basket, the t-shirt, then maybe you don't need to represent everything, every point on the t-shirt, right? So depending on the task, the resolution that you want to represent the state of the world should change. We shouldn't always use the same resolution. And that applies to mobile manipulation as well. When a robot goes into a room, there are hundreds of movable objects in this world. And if we want to represent everything in our state and plan in environments with everything, then that is going to be too costly. What we do today as researchers is that we cheat a little, and we actually, in our research, we say, oh, okay, we know that the robot is going to grasp that cup on the table. So we code things so that the robot ignores everything else and focus on that cup on the table. But actually, when we have robot systems that really works in our homes, they do need to identify what is relevant for themselves and then reduce that dimensionality, right? So that is the underlying principle here. So the first thing that we did was to apply this idea to deformable object. So we have been working on this in the deformable object space. What we basically do, which I will explain in slides in a moment, but this video also shows that we have the goal. It is task dependent again, but from the goal we extract a simplified model, and we plan with the simplified models, the reduced models, and then we try to plan with those simplified models, just so that the planning is a little bit faster than planning with the full model. Okay. So here, for example, the task is to fold this towel diagonally, and it has been. This is just an execution of the plan that we have come up with, but the underlying system is working in a way where it reduces the dimensionality, as I mentioned. So basically, if you have this towel, if you want to plan with the full model of the towel, these kind of models are extremely expensive. So it can take actually hours to plan with such a model. But if your task is to fold the object diagonally, then maybe you can only make do with such a model and plan with it, right? So what we have is we have a system to extract some, again, key particles from based on the goal, and then we build a model, dynamic model of the object based on those key particles, and then we plan with that. And we actually do this in an iterative way. So if our task is to fold a towel, this is now side folding, not diagonal folding, then we do not use the original model. What we do is we extract a simplified model that you see on the top, and we plan with that simplified model. And then we check the plan on the original model. We don't plan, but we check it, and we see where it ends up. If it is not satisfactory, in this case it's not satisfactory, then we use all that information to give a bit more detail to the simplified model, and then we plan with that simplified model, and then we again check on the original model. If it is not satisfactory, then we add a little bit more detail, and a bit more detail, and then at the end we have an execution on the original model that is satisfactory, and then that is what we return. So we add detail to the model only as much as we require for the task given at that point. So yeah, different tasks that I should wrap up, given the different tasks that we have tested on, and basically we were able to show that, so the CM original one is using the original high resolution models. Simple is using the simplified models planning. You're able to show that we can actually reduce the costs, so optimize in a much more efficient way for many of these tasks. Good. So yeah, but overall, what we are interested in thinking about physics and the cost of it and how to avoid paying the full cost. And I think the key message is we don't always need high accuracy physics. We need to adapt to the task. And also the dimensionality, these are related, but the dimensionality of the representation that we use needs to adapt to the task as well. And yeah, that's it. Thank you.
Thank you so much for the presentation. I think we have time for 2 or 3 questions.
Hi, thank you so much. At the very beginning of your presentation, you have briefly shown the interaction between deformable objects and rigid objects.
Yes.
How did you do this modeling, and how do you think this can be generalized into open vocabulary for the more generalizable daily tasks?
Sorry, I understood until the last sentence. The last question was?
So, like, how do you think in the future we can make this more generalizable for open vocabulary of objects?
What do you mean by open vocabulary of objects?
It means that we do not know the semantics of the object, therefore we cannot have any explicit priors on that, like about their rigidity, etc.
Okay, okay. Very good question, yeah. So we do, like, so the mix of rigid and deformable objects is what drives us. So we are looking into that problem, and we have works in the progress looking at that. That is a challenging problem, and that relates to kind of what you mentioned at the end. So how do you represent all that, right? And right now, the thing that we are doing is looking at simulators that can represent both rigid and deformable objects, and then trying to use some of the methods that that I have presented here, which is about approximating the physics to make it cheap. But actually, I think looking long term, like if I have to give a philosophical answer, I think the more fundamental solution to that is to recognize that what is a rigid object is also basically a dimensionality reduction method that we, as the researcher, apply to the problem, right? So we actually know that the object is rigid, and then we say, oh, I don't have to represent it as a high-dimensional thing. I can reduce on the physics of it. But I think ideally, what we need to do is we need to have methods that can do it themselves. So in the sense that it may be a rigid object, but if you hit it hard enough, you may be able to break it, right? So nothing is really rigid in that sense. And so the question is, if I avoid simulating everything using rigid by the dynamics, but if I give you an FEM simulation, are you going, and then I give you a task, if the task is to push a more or less rigid object from one point to the other, then your planner should reduce down to a representation that is like a rigid by the dynamics simulator. And if the task is to divide that in, if the task is to cut the carrot into two, then it should probably reason about the deformable nature of that object as well. So we need to unify these, right? We need to have representations that unify all these and make simplifications that currently the researchers do and implement in the system by algorithmically, basically. So that is the, I think, long-term answer to that.
I see. Thank you so much.
No problem. Thank you.
Hello.
Hi,
Mehmet. Thanks for a great talk. What is the difference, like philosophically, between using these approximate physics-based models or learning the model from the simulation, like many other people doing kind of?
Learn the model from simulation, particularly, not the real world. Is that, why did you say so?
Yeah, yeah. I mean, as in like all the kind of sim to real approaches and learning simulation.
Yeah. I mean, I think the question, so the thing is, of course, there has been a lot of interest in reinforcement learning and simulation and trying to apply it to the real world. But I think one thing that we have to realize is that unless you are doing RL on the real system, if you are doing RL in Mujoko or Isaac Jim or whatever, you are doing model-based optimization. I mean, sometimes I see students saying, oh, I don't do model-based optimization. What do? I do RL. Okay, where do you do that? I do that in Isaac Jim. Okay, you're doing model-based optimization, right? The difference is that you are doing it offline. So you're generating lots of data. And then you're trying to reduce it down to a policy so that when you're executing online, you don't have to run all that costly physics, right? But then you have the generalization question. Okay, how well does it generalize to the task that you have in front of you online? And that is where the neural networks have been helpful. That is like, that's why we are looking at that. Like, they generalize good enough that we can do that. But I think it is still a challenge, that issue. Like, there are cases where they don't generalize. I haven't seen an RL work or the most recent behavior cloning kind of works where it generalizes to things like, a box of objects, many objects, deformable, rigid. That kind of generalization we still haven't seen. So I think it is useful to explore both directions: the offline direction of running the computationally expensive physics offline to then compile it down into a policy to use online, versus trying to optimize online. I think we need to meet somewhere in the middle, but both are useful. And the difference between them is not one is model-based and the other is not model-based. I think they are both model-based, yeah.
Yeah, thank you very much. And maybe if I can add one sub-question.
Yes.
In terms of sim to real, apart from the generalization issues, in terms of sim to real problem, do you also have kind of similar problems sometimes using these approaches, or is it?
Of course. I mean, I think the question of, like, whether how good the simulator translates to the reality is an interesting question. Therefore, I think learning from the real world is actually, that is where it becomes really useful, and you need to augment your physics predictions with the real physics that you are working in. That is one way to deal with it. The second way to deal with it is, again, to realize that as long as your predictions are good enough, most real-world tasks don't necessarily need very high accuracy fit to the real world, but they still have to be good enough. And may I add one thing? Like, I think one thing that we are missing a lot is if we, we, for example, generate actions that are robust to uncertainties in our physics predictions, right? So if I need to hand you this phone, I don't try to hand it in like this. I hand it in like this. And the reason is that this is a very unstable way of moving it, and any error can lead to a failure, right? Whereas this, even if my predictions are very inaccurate as I move, this is robust. So if we look at robust planning and robust optimization approaches, I think we can address that gap of sim to real more and more. I think that is another way, another thing that we are not focusing on that much. Yeah.
Thank you.
Yeah.
Maybe one very short question.
Okay.
Regarding the second part of the talk, when planning with simplified models,
yes,
how do you know how to find these simplified models? Is it learned somehow? Is it based on expert knowledge currently?
Good question. So I think, I mean, in this work, what we do, I can explain, but I don't think it is the a final thing proposal for me. But in this work, what we do is we look at the goal and also the current state of the object, and we extract. Basically, we fit a simplified geometric model to it. We look at the minimum number of triangles, tri-mesh model that we can fit onto that goal and the initial model, and then we merge it, and then that is the dynamics model that we come up with. And then when we, as I mentioned, we do this iteratively, and then we execute on the original model. And then if it is not good, we look at the original model and we extract what are the details on the cloth that we still need to represent to go from that current state of the original model to the goal. And we keep adding those details to the simplified model until we have something that reaches the goal. Does that answer the question? Is that clear?
Yeah, so you need some experts to know how to refine and simplify currently, at least, right? It's not learned from.
In this case, it's not learned, but I think that is something where learning can be really, really useful. Definitely, yes.
All right, thanks.
Yeah, thank you.
All right, let's thank the speaker again.
Yeah.
And next we have Maren Bennewitz, who's currently a professor at the University of Bonn, who has been conducting a lot of research across vast areas spanning navigation, active perception for legged and wheel robots, as well as detecting humans and analyzing their motions and preferences. And we'll just give her a second to get set up.
Do you see it correctly also on your screen? Okay, perfect. Yeah, thank you for the nice introduction. So my talk is about which actions to execute to gain more information about the scene in front of the robot. And this is, of course, relevant for any application where occlusions appear, where the scene has to be observed from different angles in order to ensure sufficient coverage about the environment. And in constrained workspaces, also manipulation actions might be necessary. For example, to move aside objects in front in order to uncover occluded space behind those objects. And this is called interactive perception. So for such problems, we exploit the following methods in our research. First, of course, viewpoint planning to how to choose the best perception actions. Then shape completion of objects in order to estimate the volume of partially detected objects and guide the viewpoint planning. We perform also action simulation and estimate the corresponding information gain in order to choose the best actions. And as I said, we also need to couple perception and manipulation actions in order to achieve really interactive perception, so uncover spaces behind objects that are occluding. And today we consider two application scenarios. So one is a household scenario, like objects in a shelf that need to be mapped and retrieved. And the other application scenario is from the agricultural domain, like mapping of fruits on crops in glass houses. So coming to the first application. So here we want to learn maps of objects in confined spaces, such as shelf boards, for example. And here the challenge is that we have many occlusions, as you can see here in the scene, and the scene can only observed from the front, which is very constrained. So in this scene, most probably there are objects hidden behind the two large boxes, and the robot has to reason about which actions with perception or manipulation actions to execute in order to be able to also map the object behind those two boxes. However, it is important that the manipulation actions that are carried out are carried out carefully, so that they maintain the overall arrangement of the object. So the overall structure of the scene should be maintained, since the object should not be arbitrarily pushed around on the shelf, since humans typically have certain orders in which they arrange the object on their shelves. As an example, consider the scenario. So here the robot needs to move aside the occluding box in front because some objects might be behind it. And a push to the left would result in a drop of the bottle next to it, which is not desired, of course. Whereas a push to the front would first rotate the box and then safely uncover the hidden space behind it. And that is exactly what we want to reach in our work. So we developed a framework for object mapping and object discovery in confined spaces, where we use viewpoint planning and minimally invasive push actions to reduce the uncertainty of the map representation of the environment and to uncover hidden objects behind other objects occluding them. So our system comprises a 2D height occupancy map of the environment, like can be seen here. And additionally, we trained a reinforcement learning agent for viewpoint planning that chooses the best view angles to cover the shelf. And then we learn a push prediction network to determine the best manipulation actions in order to move aside occluding objects. And I will explain all those steps in detail now. So we have a RGBD camera mounted on the robot's end effector, as can be seen here. I increase the pointer. So here's a RGBD camera on the robot's manipulator. Then the acquired point cloud is projected onto a 2D occupancy grid map. And additionally, we record the maximum height of each cell to estimate object occlusion based on the different heights of the object in the shelf. And then we train a reinforcement learning agent for viewpoint planning. The possible actions are sampled within a space in front of the shelf, and the reward consists of 3 terms. So first, we want to increase, of course, the information gain about the environment. So this factor favors views that reduce the uncertainty. So here we consider the percentage of reduced unknown map cells. Then we have the motion cost, which of course promotes efficiently reachable viewpoints. We want to reduce the motion cost of the arm. And we have a penalty for object collisions or object drops, because this is what we do not want to achieve. And we use the map's latent space of the environment. So we train a variational autoencoder with 32 dimensions. We have other relevant features as input, like the last viewpoint that was executed and the center of the maximum unknown area in the current map. Those are also used as observations in our viewpoint planning agent. And finally, the output then is a 5D viewpoint that the robot executes next to observe the scene. As I said, we also have a network that predicts minimally invasive push actions that cover hidden space. So here we generate push proposals via raycasting on the grid map of the environment. And the push prediction network is learned in a supervised manner and then suggests the best push. And yeah, how this push prediction network is learned, I explain shortly. So we use push proposals labeled by humans, and the labels indicate expertise regarding uncovered space and preferences regarding scene changes. And we have such images labeled by humans. These are height maps of the environment, like the current state of the mapped space, let's say. On the left, we see several objects have already been mapped, and here's a large unknown area behind those objects. And this is one push proposal proposed by our system to the human, and the user can now label it either as a good or a bad push. And in this case, it would be a positive example, so a good push, because if this object here is moved slightly to the left, then the large unknown area is uncovered and no object collisions occur. And when in the same situation, for example, this here, the red arrow would be the push proposal. This is a negative example because then several collisions would occur, and this is not what we want. And such input images with labels are used to train our push prediction network. And during runtime, during execution, our push prediction network is then used to estimate or to suggest the best push to the robot. So to summarize, our approach uses the occupancy grid map computed from the acquired point cloud for viewpoint planning, as just explained, and also for push prediction. And in the end, we perform action selection. So we decide whether to execute a perception action or a manipulation action based on the resulting entropy reduction after the executed action. So if the viewpoint planning does not achieve any entropy reduction anymore, we switch to the push prediction and execute the best push. Otherwise, if the viewpoint planning can still reduce the entropy, then we continue the viewpoint planning. Of course, this is a simple heuristics, but it works quite effectively in our experiments. So first, we evaluated our viewpoint planning agent without the pushing, just to show how well the agent learned to perform perception actions in comparison to two state-of-the-art methods. So one of the state-of-the-art method is a next best view planning approach, and the other is a global planner. And first, we used 3 static viewpoints to compute an initial map. We did that for all the 3 approaches, and then calculated the entropy reduction after the viewpoint planning terminated. And as can be seen, our trained agent achieves the entropy reduction of 30%, which is much more in comparison to a random agent and also to the 2 baselines. And these results were first evaluated in simulation, but we also verified them on a real system. So this was to show that our viewpoint agent produces good perception actions. And next, we evaluated also the effect of the pushing actions. So here we evaluate the whole viewpoint push planning pipeline that includes also push actions if the entropy cannot be reduced anymore using viewpoint planning. So we here tested the additional entropy reduction after several iterations that contain also multiple pushes. And here we compared our approach to just a random push selection. And as we can see, we achieve a high, or both approaches actually achieve a high entropy reduction compared to the initial map. However, the random push, when executing the random push, we have a high object displacement of 34 centimeters, whereas our approach reduced the object displacement compared to this random approach. This is important because we want to maintain the overall scene structure, the overall configuration of the objects on the scene. And also the random push execution leads to a very much high number of object drops and collisions, whereas we only have like 4 object drops. So this showed that our pushing agent or our push prediction network can actually reduce the entropy and also achieves only few displacement or object drops. So here I have a video demonstrating our performance in practice. On the left, you see the real scene with the robotic arm, the camera, and the executed actions. In the center, you see the in-hand view of the camera. And on the right, you will see how the occupancy grid map evolves when the robot carries out the perception action and the pushing actions. So first, the robot carries out perception actions, updates the occupancy grid map, then generates push proposals on the current map. The robot executes one first pushing action in order to unveil space, carries out soon a second pushing actions, and then is able to retrieve the box which was hidden behind the other objects before. So what we are currently working on is point cloud completion. So based on 3 initial views, we calculate a combined segmented point cloud and then complete the point cloud using the pointer network. And we want to use this information first for viewpoint planning, to guide the viewpoint planning, but also to have humans labeling or demonstrating their pushing preferences using the segmented point clouds. So here you see example pushes demonstrated by human labelers. These are the 2D projected points of the completed point clouds, and users can now easily introduce the agent to their preferred pushing actions that do not change the scene too much. And we want to use those information as input to further improve our prediction network for the pushes. What we also want to do in the future is, of course, to extend our approach, which uses currently a static setup, to a mobile manipulator, which means that we have an increased action space for viewpoint planning and for pushing. And we want to learn, of course, the best placement for the base of the robot for the perception and the manipulation actions. So if the robot is more placed on the left or right side of the shelf, it has more versatile angles to observe the shelf. And if it's more distant, then it can also cover different shelves at different heights. And if the robot is closer to the shelf, then it can perform better pushes. And we want to include this information and learn the best base placement in the future work. What we also want to do is we want to combine learning with reasoning and planning. So as I said, currently we use a heuristic to decide whether to carry out a perception action or a pushing action. And this might lead to inefficient behavior, even if we showed quite good results. And our new idea is to model the problem as a MOMA.v2 and reason about the outcome of the different action types in a principled way. Of course, that complex belief updates are typically done via Monte Carlo methods, and drawing samples from complex dynamic systems is too computational expensive. So to reason about perception and pushing actions, update the map belief, and ultimately come up with a sequence leading to the minimal map entropy is not computational intractable. And therefore, we want to apply a deep learning approach to update the belief after executed actions. So we want to use neural networks to estimate the intra-cell dependencies of the map for both map completion after perception actions and action consequence prediction of pushing actions. And then we sample push actions to predict their consequences in the map space using the neural network. And we also sample perceptions actions based on the predicted map, and then use the neural network in order to update the map belief. And in this framework, we will then have means to reason about the outcomes of the actions and choose the best one. So now I come to the second part of my presentation, which tackles the agricultural domain. So here we consider active perception for robotic harvesting. And of course, accurate mapping of the fruits, like in this case, sweet peppers, is key to yield estimation and also to carry out robotic harvesting. But we have several challenges here. So first, the environment is quite unstructured. So we can not apply learning techniques because the environment is too complex, but we'll use a standard control-based method. We have many large occlusions. As you can see, for example, here, behind this leaf is actually a sweet pepper hidden that needs to be recognized by the system. And we have a very constrained workspace, which means like typically the crop rows are arranged in rows in a glass house with only little space in between, which means that we have only limited maneuverability for the robotic arm, and we have to do good motion planning here. What we use here is next best view planning with shape completion, which means that when we have partially detected fruits, we estimate their shapes using super ellipsoid fitting. And then we use unknown regions of the completed shapes in order to guide the viewpoint planning. So we generate viewpoints that cover the estimated regions of the fruits in combination with exploration sampling, of course, to detect new fruits on the crops. And our idea is that we synthesize information-rich viewpoints and use the missing surfaces of the completed shapes of the fruits to generate viewpoint targets. So as an example, on the left here, you see partially observed fruits. On the right, you see their completed shapes using super ellipsoid fitting and uniformly sampling of points on the surface. And then we use this information in order to determine the next best view in order to cover the estimated backside of the fruits to get a good estimate of the shape. So in this example, a promising view would be the indicated one here. And we estimate the best viewing direction from the completed shape geometry. And if this is not reachable by the robotic arm due to occlusions or collisions that occur, then we choose a close-by view that points in a similar direction to cover the missing part of the fruits. So to calculate the next best view, we use the information gain based on the missing surface area that might be covered when we execute the view. And of course, we also consider the motion cost of the arm to reach that viewpoint. And we only consider viewpoints that have a utility score above a certain threshold, and otherwise we perform exploration sampling, because when a fruit is covered, then of course we need to detect other fruits on the crops. Switches to finding new fruits, and this leads to a higher volume accuracy estimate of the fruits compared to baseline approaches that do not use the shape completion method. And we have a significantly lower computation time compared to the baselines, since we use viewpoints because we perform this view synthesize using the completed shapes and do not apply the viewpoint sampling and raycasting as the baseline. So we have a lower computation time. And here I have a video demonstrating our system and a short video in a glass house. So on the left, you see detected the point cloud and detected fruits and their completed shapes. And on the right, you see the system executing the motions. So you see the colored point clouds illustrating the completed shapes. And this approach is also used on our newly developed harvesting robot. So here the robot performs perception actions in order to detect all fruits on the crops, then performs the shape completion in order to be able to estimate the volume accurately and also to grasp the objects. So now the robot approaches a fruit with the manipulation arm and would be able to cut it. So this works quite well. But as I said, we currently only calculate the next best view. And so we only perform one step look ahead. And this can lead to inefficient arm trajectories because the arm might need to reach different viewpoints that are far away, right? And so especially in highly restricted workspaces, we also have challenging on the motion planning because collisions might occur. And to deal with these problems, we also need to consider the motion cost in a more principled way and perform better motion planning. And our idea was to not only look one step ahead, but for a sequence of like 5 seconds or so. And to do a planning for a sequence of 5 seconds, we developed an approach that uses a graph-based view motion planner, which means that we combine motion and view planning and take into account efficient motions between the different view poses. So we integrate and connect nearby poses, nearby views into a graph, and then search the graph for a sequence leading to the highest utility, thereby considering sequences, as I said, like 5 seconds execution time. And in this way, we are able to generate information-rich view sequences that are also efficiently executable. And in this way, we are able to integrate more views within a given time budget compared to standard next best view approaches. And this approach is also especially useful for constrained workspaces, since we have this component that considers the trajectory of the arm and considers sequences of viewpoints. So we deployed the system in our glasshouse. You see here on the left the real robot, on the top right the current camera view, and here like a motion graph that is constructed during operation. And the trajectory in cyan is this trajectory of 5 seconds length that is currently executed, but the map is constantly updated and this graph is constantly recalculated as new observations arrive. And the robot first spends a certain amount of time in one segment and then moves forward to the next segment in order to map all the fruits. This continues until the end of the crop row is reached. So, still with standard viewpoint planning, many occlusions remain due to the leaves which are in front of the sweet peppers, like in this example here, for example. And we need manipulation actions also in this application scenario, similar to the shelf one, to move aside occluding leaves and detect the sweet paprika, or to be able to estimate the size of the sweet paprikas behind them. And we developed a system which contains our perception module, which does the semantic segmentation and the shape completion, as just explained. And then additionally has a planning module which generates possible grasping points on the leaves and possible pulls to be executed by the robot arm. And then we perform action simulation and predict the visibility of the fruit behind the leaves and choose the best action to execute in order to increase the visibility of the fruits that are currently occluded. Here are a few more details and an example. So given this is the current situation, we have detected the fruit behind a leaf. Then the robot determines possible actions. So it determines first possible grasp points on the leaves and possible pull actions to execute. It simulates the actions, estimates the deformability of the leaf, and also estimates how much of the fruit behind it would be visible when executing this action. Then we compute like a visibility score and choose the best action to execute. So in this case, the action to pull the leaf up would be the one with the highest score, and the robot would execute that one. And after this action, as we can see here, the visibility of the fruit increased significantly. So similar to the approach before, we also have to reason here about when to execute perception actions and when to execute push actions to increase the visibility. So to summarize my presentation, presented interactive viewpoint planning approaches for mapping of objects in complex and confined spaces. We first considered the shelf domain, where we have a very constrained environment which can only be observed from the front. We developed here a reinforcement learning framework for viewpoint planning and also learned a network that generates minimally invasive push actions. The push prediction network was learned from labeled data by humans, and it incorporates human expertise and preferences regarding scene changes and the uncoverage of regions behind other objects. And we showed in our experiments that the executed push actions highly benefit the viewpoint planning while maintaining the overall object configuration. So we only have slight changes on the scene, which was a requirement here. So in the second application, the mapping of fruits on crop rows and glasshouses, we also estimate shapes of partially observed objects and then use the completed shapes to guide the viewpoint planning and increase the reconstruction quality of the fruits. And we also combined motion view planning to generate information-rich and efficiently executable trajectories. So here we use no learning-based approach, but a classical approach, since we have a very complex environment, and a learning-based approach wouldn't be feasible. And as I just explained, so we also want to integrate the manipulation action into our system to move aside leaves and cover hidden fruits. Thanks for your attention.
Thank you very much for the great presentation. I think we might have time for 1 or 2 questions.
Sorry, you are the first.
Thank you for the presentation. For grasping the leaf, so did you use some geometry for the grasping planning, grasping position? How to decide the grasping pose for the leaf?
Is the question regarding how I detect it or how I estimate the deformability?
Yes, my question is how to grasp the leaf to improve the visibility of the kind of vegetable.
So first the leaf is detected, and then we consider like different possible grasping points and generate pull actions. And then we estimate how the leaf deforms using some method that calculates the deformability. And since we use shape completion for the object behind the leaf, we can reason about how much of this object would be visible when we execute the action.
Thank you so much. So in that case, no kind of prior information for the leaf, just using the observation.
Yeah.
For grasping. Right. Thank you so much.
This is ongoing work, and we will submit it soon. I can send you the paper if you like. You have to send me an email then.
Thank you so much.
Tamim? If it is allowed.
Of course.
It was about how do you estimate the deformability?
This is an approach, let me think. It's quite computational expensive. It's from 2007, was developed by ETH. I can send you the link of the paper. It's one drawback that it takes a long time to estimate, but it's very accurate. But we have to see how we can speed up that. But I can send you the paper if you like.
Maybe one very short question.
Thank you, it's a brief one. I was a bit surprised that you grasp leaves at all instead of trying to push them out of the way, which is the way a human would probably do it. Can you elaborate for a bit why you decided to do that? Did you try push and it's too unstable, or?
Can you speak a bit closer to the mic, because I didn't understand it.
Sorry, there's a lot of echo.
Yeah, very much better.
I was a bit surprised that you grasped the leaf at all instead of trying to push it out of the way a human would do it. Did you try to push it out of the way and it turned out to be too unstable, or did you directly go for grasping it because it's the way roboticists
First we simulate it, and then we really pull it away.
Yeah, just push it out of the way without grasping.
Why not push it? Of course, also possible, but this is typically not done or cannot be executed in a very controlled way, right? So grasping it is more reliable. But of course, it would be also an option for large leaves, maybe. Yeah.
Thank you.
Good point.
Okay, great. Thank you very much.
Thank you
for that interesting presentation. And next up, we have Keerthana Gopalakrishnan, who is a senior research engineer at Google DeepMind and has worked extensively across big data and transformer and large models. You might know some works of hers, such as SEIKEN, RT1 or AutoRT.
Perfect.
Hi, everyone. Let me just keep track of time. I'm Keerthana Gopalakrishnan. I'm a senior research engineer at Google DeepMind, and today I'm going to be talking to you guys about how large models can transform robotics. I'm going to try to keep my talk on the short side, just so we can have lunch on time. All right. So robotics and large language models. So in the past few years, large language models and large vision language models have been making waves in AI, but also in lots of different spaces. And we think that robotics is one that can be disrupted effectively by this technology. However, robotics presents a very specific challenge to training large models. First is that real-world data collection is kind of difficult to scale because it is bottlenecked by the availability of humans. And you need human demonstrations in order to scale these models. The second is that people have tried autonomous collection using already smarter policies, but the downside to them is that they need a high level of bootstrapping. You need them to either work in sim, or you need the model to already be performant in order to start collecting autonomous data. And also, people have looked at sim-to-real approaches, but the challenge in sim-to-real is that if you have to make a very realistic simulation of the real world, this is very challenging and very compute intensive. And especially for robotics, you need to model physical interactions, and modeling that physics can be tricky. Regardless, how do we look at modeling robotics using large language models, and how do we wave the ride of the AI revolution and try to see how far we can push robotics and solving robotics with that? So in this talk, I will be covering some of the highlights of our work in the last 1 year. But to better understand that, we also have to look at what has happened until that point. So I want to introduce our work SayCan from 2022, which looks at planning for robotics with large language models. So here you ask a robot how to get a drink from, bring me a drink from the fridge, and then the LLM makes a high-level language plan that the robot then executes. And here we use an affordance model to decide which part of the task sequence to execute based on how likely it might be to succeed based on the initial conditions and the task that the robot has already been trained on. However, SayCan is a high-level planning model, and it doesn't have the motor skills to actually execute the task. So then comes RT1, Robotics Transformer 1, and this was released in December of 2022. And this is a scaled imitation learning model, which uses a language condition policy. So you show a transformer model images and also language instructions, such as images from the robot's camera and language instructions like pick, cook, can. And then you try to train it on the action tokens. And then lastly, there's POM-E that came out in March of 2023. And what this model does is it is a planning in multimodal space. So it also has vision. And this is planning in multimodal space is better than planning just in language space. But POM-E also does not have motor skills, so it still uses RT1. So the way that you can think about scaling robot learning with large models, you can think of, there are two parts to it. The first is scaling policies, which is keep the data constant and what might be the improvements I can bring to policy performance by using large models, by using better representations, better abstractions. And then secondly, we will talk about ways to scale data and maybe some hacks for it, and also things that we have learned from past data collection efforts. So firstly, scaling policies. So one way you can think about scaling policies might be to scale policies with VLMs. So VLMs encode a lot of world knowledge about the world. VLMs like Pali, like POM-E, like Gemini. And up until this point, we had been using RT1, which uses images and text and converts those into discretized actions. But we can use VLMs directly as a policy. But the challenge becomes, how do we make VLMs speak the language of robot control, low-level robot motion generation? So here, the way that we sort of attach robotics to VLMs is by encoding actions into action tokens in a language space that VLMs can already talk in. So for each dimension of the action, for each degree of freedom, we have one token, and then we have an extra token for terminating the episode or not. And so this was done for the Google robot, the everyday robot, and here we had 3 variables for the position of the end effector, 3 variables for its rotation, and then 1 for like gripper open close. So we discretized this into bins that have 256 dimension size, and then convert that action into a bunch of strings. There are different ways of encoding actions. You can also use like the least used tokens of the VLM, but this is what worked best. And then this is like a generic way to train on top of most VLMs. And for this study, we use Poly, a 5B model, a 55B model, and also PalmE, a 12B model. And the data set that we used for this was web data, Webly, and also robot data, so which was used in the RT1 paper, and it was collected with 13 robots over 17 months and had 130,000 demonstrations. So once we train like this, we see that the robot actually exhibits a bunch of emergent skills. So what are the categories of these emergent skills? We see that robots are sort of able to understand symbols because these symbols are present on the internet, and we can now use them or compose them during motions. So for example, it can understand what is the flag of Germany. So you can say, move Coke can to Germany or move banana to Germany. It can understand who Taylor Swift is, so that's human recognition. To an extent, it can also do a little bit of math. This is my favorite result from this paper. So you can say, move Coke can to the sum of 1 plus 2, and then it'll move it to 3. And we see that symbol understanding, reasoning. So reasoning as in, like, you can say, pick up the healthy snack or pick up the extinct animal. And it would reason that you are talking about an orange instead of a chip bag or a dinosaur instead of a dog. And we see that this performs better over RT1, and also that the larger model performs better. And then we compared against other baselines as well. Now, you can think that the motion skills still come from the robot data set. And while the large vision language model reduces the demand for generalization data, you still now need to collect a lot of motion generalization data. In the past, a lot of robotics research has focused on generalization, and we had collected a lot of data to adjust for different lighting situations, background changes, to understand what is a Coke can and a Pepsi can. But now we see that with internet scale models, you get a lot of this knowledge for free, and now you can really focus your data collection on actually improving the motions. So this is, you can think of it as like a gain towards the efficiency of data collection and focusing it towards now areas that VLMs might not be able to do well at. We also see that with RT2, there are signs of chain of thought, which means you can add some data which involves planning, and then you can jointly train on both planning data as lower latency. Think of this as pointing towards a future where one model can do both high-level planning as well as low-level motor control. So here the example is bring me a drink, and then it makes the plan pick 7-Up can, and then it also predicts the action as well as the plan. However, RT2 still uses human demonstrations to learn motion data, and human demonstrations is very high quality data. And we might want to think about how to scale with negatives. So there's a lot of robotics data that's collected in the real world, but a lot of them also end in failures. And most of this data is thrown away in an imitation learning regime. So last year we came out with this paper called Q Transformer, which tries to use negatives on top of imitation learning methods like transformers. So there has been prior work in this area, like decision transformers, which tries to model the state action reward and then trains the transformer on these sequences. But we find that, like for decision transformers, the performance falls as a function of the amount of negative data that you add. So it is really hard to argue that the model is actually improving from negative data. And improving from negative data is necessary for, say, recovering from bad states, etc. With Q Transformer, what we do is that we predict a sort of a Q function, and then we take the action that maximizes that Q function. And each dimension, for the prediction of each action token, we predict a different Q function, which has the same dimensionality as the action tokens. Unlike this, in regular RT2 and RT1, you actually take the action that maximizes the probability in the training data set. So this is slightly different because you are optimizing over a reward function on the data set. This is still an initial result, and we think that it is important to sort of bring the advantages of reinforcement learning onto an imitation scaling regime. So reinforcement learning has some very nice properties, which is that you can synthesize better policies out of like cheap policies, because you can do some sort of trajectory stitching, but you lose this ability once you go to large imitation scaling regime. And so Q Transformer can be thought of as an idea to bring trajectory stitching or optimizing over rewards to the transformer era, but more work remains to be done to figure out how to optimally scale this on top of really, really large models. Another way to think about how to get maximum performance out of these models can be thinking about what may be better representations. So we came up with this paper called RT Trajectory, and what it does is that in addition to the RT1 data, which is a sequence of images, language, instruction, and action dimensions, you also add this additional frame, which is a trajectory. So you represent the motion, and then you represent an encoding of contact interactions. And we see that just adding this one dimension sort of makes your model focus on that, on those motions. And then you see that at inference time, now you can prompt your robot in a very different way and try to come up with new motions. We also see that with this technique, you can do now inference on human videos as long as you are able to sort of map the trajectory of the human hand. And you can also make a robot execute trajectories that are drawn by a foundation model, either via code or just via generation. So on the bottom are new motions that were not present in the RT1 dataset that RT Trajectory is able to do by just still training on RT1 alone. So by making the model pay attention to these lines and these contact interactions, now you can prompt your robot to just do those things and control your arm in a way to execute these trajectories. And we see that this is the method this method even has more motion generalization than RT2 itself, because RT2 still can only do, while it does improve on image and language generation, it still relies on the robot data set for motions. And RT Trajectory sort of increases the yield of motions from the same amount of collected data by hindsight relabeling. Now, let's move on to the second part, which is scaling data. So one way we can think about is scaling data by pooling. And this is a paper that's appearing at ICRA, so I would encourage you to check it out, OpenX embodiment and RTX models. So this was a large collaboration with a lot of different robotics labs. And we have we accumulated a data set of 1 million plus episodes over 22 different robot embodiments, 34 research labs across the world, and 300 plus different scenes. And the thing that I really, really like about this is that robots can sort of learn from each other. And we see early signals that maybe robots are not that different from each other. Maybe they are only as different as Chinese and English, or as different as languages. And a lot of core concepts can transfer. So the way that we do the study is we use the RT1 model and RT2 model, and then we modify them to RT1X and RT2X, the X to represent cross-embodiment, which means now that you train on lots of different models and encode them kind of in the same space. And we see that training on a large data set also improves in distribution performance. So these models were performing better than individual models that, and individual RT1s you can train on the data sets of the corresponding labs, which is a really cool result. And also, you can think of it as a data set can be thought of as an individual lab's data set can be thought of as sort of like pointing in certain directions, which means that it specializes in a certain way. And by pooling all of them, you can bring all that skills together in the same brain. So now you can think of it as this may open a path towards building sort of like a generic robot brain in the future. These are still initial results, and we still need to de-risk a lot of different aspects. And you can also think that using or starting from a large pre-trained checkpoint can already reduce the amount of data you might need from your own robot in order to reach the same level of performance. We also see that scaling data by collaboration leads to some emergent skills, which is that skills transfer to the Google robot. And we see there are 3 categories of it: absolute position understanding, relative position understanding, and also like putting things into receptacles and stuff. Next, I want to talk about scaling data via language-driven exploration. So in RT1, we found that if you collect a lot of different data, you can get very high in distribution performance. So we were thinking, well, how about let's just collect a lot of data with a lot of different robots? And we also see that at the moment, scaling robot data sets, you kind of need to also proportionately scale the number of humans deployed, because you need humans to control these robots. So robot data sets only scale linearly in proportion to the human operators that are there, but we want to scale faster than that. So what we do here is we use vision language models and language models to sort of explore the space, come up with goals for robots, and then use an underlying policy to collect for it, and then train on it and study various properties of it. Now, we see that once you have an LLM that is generating goals for robots, it brings with it a high degree of semantic steerability. So for example, you could say, collect gardening tasks today, or collect cooking tasks, and the fleet can sort of optimize for that goal. You could also, and once you start running them in realistic situations, safety becomes an important thing. So for example, it can, you sort of have to model these robots to like not harm people. And the way that we do it is by using Asimov's laws and then explaining that to the robot, and then making sure their reasoning is coherent with those laws by asking it to critique itself. We see from AutoRT that now we can sort of, one human can control 5 different robots, which can increase the yield of your data collection. We also see that LLM tasks are semantically better than compared to other baseline methods of collection. And we also see that sort of prompting with a robot constitution improves the safety of LLM-generated goals by 3x. On the bottom are some learned policies executed by the robot in this way of collection. However, this was just a first experiment, and we learned a lot of different things about what to do and what not to do regarding data collection and scaling data collection. So the first thing that you have to think about is that while you collect data, you can't just go ahead and collect a large data set and then start training on it. You have to validate the data set by learning. You have to validate the learning loop as you're training. The next thing we learned is that most people think that the most diverse data is the best data set. But the best data set is not the most diverse data set. It is not the largest data set. It is the data set that leads to the most policy improvement. And so you kind of definitely have to tie your data collection to that metric. And also, the ideal data distribution changes a lot by what is your underlying policy. For example, we found that there can be such a thing as too diverse. So if your policy is not very sample efficient, then too diverse can lead to no learning improvement. So, and there are multiple ways of improving the skills. You can either spend a lot of money by doubling your ops, or you can lower the sample requirement of your policies, and one is way cheaper than the other. We also find that once robotics is in an imitation learning regime, scaling high quality data is more important than scaling low quality data, because you can scale a lot of failures, you can get a lot of failures and stuff, but then you don't know from an imitation learning only perspective how to synthesize better policies out of it. So this comes back to the Q transformer and other methods that I talked about before. There is another way to scale data, which is by using zero-shot LLM policies. So we see that LLMs and VLMs can already understand and reason a lot about the environment. And if you can define the interfaces to robot very clearly, if you can define the task very clearly, then they may be able to generate code that can already control the robot. So this is also a paper that's appearing at ICRA, so I would encourage you to check it out. And so the robot can do things like pick up things from a dishwasher, whisk in a bowl, clean a toilet, and it has not been trained on these tasks, so it is doing them zero-shot. And this can give a sort of a clue about what may be next and how we can think about taking this much further. So what's missing? So firstly, scalable interfaces. So at the moment, a lot of these methods that I discussed use action tokens to make robotics sit on these large models. But action tokens may not be the right abstractions, because we see that a lot of failures come from making VLMs and LLMs that know a lot about the world sort of speak this very strange language. And we see that the knowledge is not transferring. So you can think of it like a funnel where you can increase the width of it, like how much world knowledge transfers to robotics. And one key intuition here is that if there is a policy which has a higher zero-shot success, that could be a candidate for your base level policy. So we see that VLMs can already do things zero-shot, so maybe we can start from there. We also think that scripting methods currently do really well in industry, and maybe there is a way to solve robot learning by teaching these multimodal models how to do very good scripting on the fly and make it very generalizable. The second thing is solving dexterity. We also see that a lot of gross manipulations, so like pick and place, opening doors, can be solved, but a lot of economically useful tasks are still about solving fine manipulation and solving highly dexterous manipulation. And what may be the breakthroughs that we need in order to solve them? So there are still some intuitions here. One is that you still have to do it while scaling data. And you can think about what may be a few Pareto optimal frontiers towards scaling data in a cost-efficient, sample-efficient fashion. And secondly, we see that dexterity involves modeling multimodality really well. And of late, there have been policies that do better at that, like diffusion. So how much can we stretch that? And lastly, taking robotics to the real world. So a lot of the results that I presented already are still from labs, But if you have toy environments, you get toy intelligence. So you really have to push robots to collect data in the real world. A lot of upstream tasks like embodied reasoning may already be solved because these models are extremely smart in reasoning about the world. So can we think about how to really apply them to robotics and how to measure the gaps based on where they are right now and how to improve from that? And can we create data flywheels that are sort of rooted in the real world and scale from there? So yeah, I would like to end my talk there. If you want to stay in touch, there's my website and my Twitter where I sometimes tweet robotics epiphanies. Are there any questions?
We can take maybe one question.
Increasingly, it seems that scaling is important for robot policy learning, and it was a great talk. I was wondering what's your view on scaling modular approaches like scaling modules such as language or image perception versus scaling end-to-end action prediction models?
So one downside to scaling modular approaches is that the modularity can become a bottleneck. So in some sense, you kind of have to make the gradient flow in order to scale the whole thing. If you sort of if you have modular networks, you can end up with little bottlenecks here and there where, let's say you have a high-level model and then a low-level model, which are not aware of each other's skills, then the high-level model can put you in places where the low-level model cannot start from. For example, in order to take things from the drawer, you need to open the drawer fully. But if an open drawer model does not understand that, then you cannot. Yeah. All right. Yeah, feel free to reach out if there are more questions.
Maybe you can take the seat for. We will do a bit of shorter panel discussion. So I would like to call our speakers. Mehmet, if you're here, Maren, and Professor Okumatsu.
So she told me they should work.
They should work. Do they need to do? I think you choose.
I'm just
Okay. You just put it on when you want to speak. Okay. Sure. Okay, we will also set up a poll while we are discussing. So I would try to keep it short, so only a few questions. So I would like to start with a fundamental question to you. How do you think we should be designing our algorithms for mobile manipulation? Because most people usually think of mobile manipulation in kind of a decoupled way, by extending manipulation algorithms with navigation or extending navigation with manipulation and in treating it in some sense in a decoupled way. Do you think that this is sufficient, or we should think of mobile manipulation as one single thing at the start of all our projects? Please feel free to take the lead, whoever wants. Yeah.
I can start with this.
Yes.
We actually did approach a mobile manipulation in a sort of modular way by working on navigation and manipulation separately and then composing them with the secant plan. And we find that now this introduces weird failure modes. Like, for example, you could say, go to the fridge and get me a drink, but the mobility, the navigation policy leaves it a little bit farther from the fridge, and now the manipulation cannot reach, or it's a little bit farther from the drawer. So I feel that you have to jointly learn in order to work together, like make both parts work rather than learn them separately.
Okay. Yes, I see that the audience also thinks that they should be combined. Mehmet, what do you think?
That combined.
That they should be combined as one single thing, but let's keep discussing
Yeah,
because
yeah.
maybe the modularity
obviously,
can help.
if we can solve the combined problem, that is the more fundamental problem, right? So I think decoupling is just a way to cope with the complexity and difficulty of the problem. So
yeah.
if we can having a solution that can address the base and the arms together, and also like we discussed, it is not only dealing with that, but like once you have mobile manipulation, you also can go around in an environment and all the different objects that you have to deal with also changes, right? So then you also have a much more foundational model that can deal with liquids and rigid objects and deformable objects. So, but then it becomes a much more difficult problem, and then you have the methods to do that. If you can, of course, I think like combined approaches is
But is it a research problem then? What do you, Professor Okumatsu, believe? Is it a research problem to try to think of mobile manipulation as one problem?
I'm a hardware researcher, so my my challenge is the back drivability is a challenge problem for us.
Mm-hmm. So the question is, does modularity help, like treating, navigation, approaching a point of interest, and then interacting with the arm is something that helps, or should it be whole body, like considering both moving and manipulating?
Yes, he's translating.
Hello, I'm his coworker.
Yeah.
I will cover the control aspect. So, if we want the mobile manipulator to do some basic tasks like pick and place task, I think it's fine to think of just mobile manipulator. But if we think further, if we expand the task variety, like contact latch manipulation task, I think we should consider mobile manipulator as
whole as one
whole
thing.
body thing, like humanoid.
Yeah.
Or
Okay. Yeah. Thank you. I will try to go to the next poll while I will start for the next question. Yep. Yeah. So, what do you think? What share of manipulation algorithms and datasets that are currently available can actually be used for mobile manipulation? Do we need to start from scratch, or does most of these datasets that exist outside there publicly can be transferred to mobile manipulation? Like, what do you think? Is there a percentage? Are there even datasets for mobile manipulation? Maybe Keerthana, you can tell us from the OpenX embodiment. Yeah, the people like change. Currently, it seems that 50% of the people think that only 30% of the 0 to 30% is is actually useful for mobile manipulation. There are some more optimistic there, 20%. No.
I think that mobility and manipulation are the same problem. It's just all about how to control the end effectors of a robot and how to do an action given a certain state. If you have a really large model, you can think of it as it can absorb that data. It can absorb both mobility data and manipulation data and then make a robot control its base if it needs to, its arm, gripper or end effector if it needs to.
Mehmet, what do you think?
What share of data? I think, yeah, the RTX work is the kind of the answer to that, right? So it is showing that even though there is variation, they can potentially be integrated into one learning framework. So I don't know. I don't know. I can just say that it is an interesting research question, actually. Like, you know, how do we actually get to exploiting data that exists? Whatever we can get from any data set, how do we extract that and put it into one large system? You know, people looking at, I don't know, YouTube videos, like, you know, that's a data set, right? So how can we extract whatever we can from that? I think that's the.
But I think do you think in the YouTube videos the skills transfer directly to us?
Not yet.
They will not, because I think the humans are extracting objectives from the YouTube videos. They don't extract the skills. This is what I mean. Do you think that by looking something, the robot will start doing it perfectly?
Maybe not perfectly, but that we can transfer still a lot of different things. And I think currently maybe the problem is that the embodiment gap is too large. And once we start closing in on the embodiment gap, it can be, the transfer may be more possible. We also see that even after RTX, there has been subsequent work which show transfer between navigation and manipulation data set. For example, with this one paper found a very interesting result, which was that indoor navigation helps manipulation. Because indoor navigation has all these like sharp corners and stuff, and then it improves the manipulation of like objects, because objects also have like sharp contours.
Okay, that would be interesting. I don't know if anybody has an additional point. And then I have a third question. Do mobile manipulators need legs, or are wheels sufficient? So do you need, for a large range, let's say, of tasks, if we think of like home robots or some manufacturing or logistics setting, do we need humanoid robots with legs, or is it sufficient to have an upper body human-like robot on top of wheels? Who would like to take this question? Yeah? I see here wheels, both. Something else. Oh, maybe flying robots.
We think that our goal is a human-like mobile roboter. It has 2 legs, but it is difficult to control, and it is difficult to keep the stability.
Yeah.
So we are now trying to wheel. So we are trying to change wheel and 4 legs, and 2 legs is completely steps for us.
Yeah. Stability is a very important thing, but who knows what will be in the future with all the humanoid research that is going on. Mehmet, do you have any thoughts on that?
I don't know. I think it depends, right? It depends on the environment, the tasks. So I don't think in this case we can say one is better than the other. Yeah, it is. You know, if you look at any mobile robotics textbook out there, they have specific sections on this where they talk about advantages of wheeled systems, disadvantages of wheeled systems, advantages of legged, and you know they apply. Like so.
Yeah. But what if you think now? We talked about the body, but what if you think now in terms of sensors connected to the body? does it make a difference what we have discussed so far? Basically, do we treat them separately? Do they have synergies? Do the data sets are going to discover the synergies and so on? What do you think of that? Because the control part is one part that has been studied a lot, but the integrated perception part is one that is one of the most challenging in general in robotics, right?
Yeah, I think it's an interesting problem, and much remains to be seen. To answer the very specific question here, I feel like legs versus wheel, the answer depends on like the scale of your ambition. Imagine that you build AGI in the physical world, and now there's a curb on a mobile robot, on a wheeled robot, and now there's a curb on the robot, and it's completely helpless. Yeah. And also you can think about like, what kind of manipulation policies might transfer at some point where you can leverage YouTube data sets and stuff. I would think that there's a lot of complex manipulation you can do if you have legs. For example, in order to reach for something farther on the table, you can balance your body. You can move your center of gravity in a certain way so that you have a higher workspace. Moving through cluttered environments require you to legs are better because you have smaller foot space, but you can do more things. So yeah, I think it makes things more flexible, and I'm a really small person, so like when I lift heavy objects, I like put my legs in a way that like the gravity is compensated for. I'm on the legs team. Yeah. Especially like if you really think about like AGI level physical capabilities, I think we need legs.
You can go very fast with wheels, though.
Yeah, people have even talked about legs with the skating.
The wheels.
Wheels and legs.
Yeah, skating kind of.
No, you're cheating.
In the regard now, because we touched on perception, and do you think that we would need to consider different kind of scene representations for mobile manipulation compared to classical manipulation and what is currently being done with nerves, given that mobile manipulation are in essence by design supposed to interact with a dynamic environment, and currently nerves are basically, you have to fit the scene and then interact with a static scene. Do you think we need to push towards different kind of representations for these humanoid, let's call them robots, mobile manipulators?
I think definitely, yes. I think that is one of the most important questions. Because, again, like, as one of the questions at the end of my talk touched on, especially when you have mobile manipulators that need to work in a large environment with a variety of objects. You go into your kitchen, there's liquids in there, there's deformable objects in there. So how do you represent it all is in a way which you can then control your actions in that representation. So I think that is a fundamental question. Yes, and there is the approaches of modeling simulators. There's approaches of nerve-like learning systems. There's the whole new world models learning approaches, right? So I think all of them are very interesting and will need to converge to a representation that works for us. But I think that is one of the fundamental questions.
Yeah. So I will. For the dynamic scene, I think it's still a nerve can be used because once scan the entire scene, and we can separate 3D mesh later and track each object separately. So I think it's nerve is still useful in dynamic scene, but we have to.
This is interesting because in this case you get like a geometric representation and then you parse it in some sense, right, to create kind of multi-object tracking. So you say, I will try to think how it evolves in time. Yeah, that's definitely interesting.
Yeah, mobility definitely introduces some unique challenges when it comes to like navigating in indoor environments, because now you have like people and stuff and you need to be fast and reactive. And especially if you're looking at it from a perspective of like large models and end-to-end learning, now you need much faster inference times than you would need if you were just like a tabletop robot in order to meet like safety and reactivity baselines. So yeah, I think a lot of research needs to be done to like figure out how to do it correctly.
Yeah, thank you. So I don't have any more questions, so I would just ask if there are any questions from the audience that you would like to address to the panelists that you think that was not asked and you would like to be asked, or something that you would, a deeper answer on some topic. Yeah, please.
Yeah, I got one. Thank you for this discussion and the great talks. It seems there is like two kind of paradigms to address mobile manipulation we discussed today. A kind of modular approach and an end-to-end one. And it seems that the most impressive results for the past few years comes from the end-to-end one, like absorbing all the complexity of the problem. But all the results, like RT2 and so on, rely on a very impressive piece of engineering, like huge infrastructure and so on. So my question is, do you think those kind of approach can actually scale beyond these great teams with huge resources, great talent and so on? Or are we assuming that at some point we'll be able to deploy those kind of models on the smartphone? Or what are your thoughts on that, especially regarding energy consumption? Thank you.
Yeah, I can take this. Yeah, definitely this is a concern because like once these models need a lot of compute and the cost is prohibitive for smaller labs, research can be just limited to large tech labs. But also we see that there's a lot of activity in the open source community on replicating these models. Like there is OpenVLA, which came out maybe I think in March, which tries to do like RT2, like vision language action models, but open source. Also, we are only at the beginning of the end-to-end learning approach, and especially with robotics. So things are going to get much better, much faster, even smaller and more, I would think more affordable. There are a lot of foundation model companies right now, and you can think that we may be heading towards a future where foundation models are commoditized to an extent. And there's a large number of them, and they are good enough. But now you can think about what may be the challenges to commoditizing robot foundation models and how we can democratize robotics data and even access to those foundation models. Yeah, I think the future looks very promising, but much work remains to be done.
Yeah, for sure. Very nice answer. Is there any other question from the audience? Please. Yeah.
Sure. So imagine the first mobile manipulation company that actually turns a profit. What do you expect that minimum viable product to actually look like? What do you think that these robots will actually do?
Sorry, what is your question again?
So if you were to imagine the first profitable mobile manipulation company, what do you think it's going to be selling these robots for?
Can I have a quick answer?
Yes, sir.
If I knew the answer, would I tell that to you?
Well, we don't know how to build it yet.
Yeah, I think I want to try to find some answer from the recent humanoid startup. So there are more and more humanoid startup recently, and I think each of the business model is different, slightly different. Some companies are trying to sell hardware itself, or other company tries to sell their resources realized by humanoid. So there are many possibilities to run business by mobile manipulator or humanoid robots. So, but Yeah, currently we don't know the answer.
If I were to guess, I think it would be like gross manipulation in retail or logistics spaces. So it appears like a lot of pick place is kind of done. And maybe one would even argue, you could even argue that maybe 40% of robotics is like pick place. You can decompose a lot of different tasks into pick place sequences. Like orange is a bunch of pick place, cleaning is often a bunch of pick place. Yeah, so I think with existing models and reasoning, maybe very nicely engineered like software solutions can sort of solve these things. I think there are a lot of companies, I live in San Francisco, so especially in the Silicon Valley, who are innovating in that space. So it's exciting, yeah.
Well, the question would be after, how do we certify those so that we can really sell them? How do we certify them safety-wise so that we can really sell them? I think that this is one of the biggest issues because, yeah, I also think that in more constrained also settings or like semi-structured, you could already now put the mobile manipulator certification. I think it's a big issue.
Yeah, a lot of industrial mobile manipulation might not need the same level of safety bar as the ones that involve a lot of interacting with people.
Yeah. Okay, yeah. I would like to then close up this session. I would like to thank our speakers. Thank you very much also for your insights. Round of applause. And I thank you also to the audience for participating. And I think you can go grab your lunch boxes before they get out of stock. Thank you again. And we will recap at 1:30, so please be back.
Okay, hi everyone. So we will start off the afternoon sessions with another set of spotlights. And Sneal will begin with the first one.
Check. Okay, hi everyone. Yeah. Oops. Yeah, just. Okay, hi everyone. Thank you for the invitation for the spotlight. I'm going to present our recent work on active perceptive motion generation for mobile manipulation. This is work at the Perl lab at TU Darmstadt. And essentially, with active perception, what we're looking at in this work is a way for a mobile manipulator to move its camera within a particular scene without any prior knowledge about the scene, and how can it effectively gather information in the scene that is useful towards mobile manipulation. So essentially, what we're saying or hypothesizing in the paper is essentially it's all about balancing exploration and exploitation. In the ACT per MOMA pipeline, which we call active perceptive mobile manipulation, we use a receding horizon planning approach, where at every time step we integrate RGBD information from the head-mounted embodied camera on the robot. We sample short feasible paths to a target object that needs to be grasped. And we select a path with the highest utility. We define utility as two, like I said, exploration and exploitation. Exploration being getting the most information from the scene. So we use an information gain metric, which is visualized over here. So which camera view would give me the most information about the target area of the scene? And at the same time, since we are working on mobile manipulation, what kind of grasp stability and reachability would this provide me? So for every detected grasp on an object, we detect whether that grasp will be reachable and what would be the cost to actually move to that grasp and actually execute this particular grasp. And if we do this at every time step in a receding horizon fashion, we have an online planning motion generation method that can balance between these objectives and provide us effective perception for mobile manipulation. This is a visualization now of it working in action. So in blue, we see many sample paths at every time step that the robot is considering. Paths include both where the base of the robot should move, as well as where the camera should move and which SE3 pose should the camera be at. And in green, it's visualized what is the best current path that the robot is executing. And everything is online and happening continuously, where the robot is adapting to new information in the scene, to new collisions with obstacles and so on, and new grasps that are detected on the object, and balancing the exploration exploitation to actually achieve this task. For more information, please find us in the poster session, and you can find the paper, code, and robot videos at this link. And yeah, thank you.
Thanks a lot. Again, I think we'll do all 3 spotlights, and then we'll take 1 or 2 questions.
Can you unshare your screen? Thank you. All right, hold on. Just need to like mirror the screen properly. All right. There we go. All right. So my name is Adam, and I'm going to talk to you about our work on fast, non-prehensile object transportation on a mobile manipulator. So first of all, what is non-prehensile manipulation? So that's just the case where the manipulated object or objects is not rigidly grasped. So in other words, they still retain some independent degrees of freedom. And in particular, we're focused on what's called the waiters problem. So that's where we want to transport objects on a tray to a desired location without dropping them or colliding with anything, like a waiter in a restaurant. And in particular, we want to be able to do this fast enough to react to moving obstacles, such as this thrown volleyball in the picture there. And we'll have a video of that in a moment. So how do we keep an object balanced while moving, where balance means that it doesn't slide or tip over, or in other words, it sticks to the tray? So our approach is to model the objects as rigid bodies. We then approximate the contacts as a finite set of contact points. We include the corresponding contact forces in an optimal control problem, and we constrain those forces to be consistent with this desired sticking mode and to be inside their Coulomb friction cones. So in the diagram here, we have 2 objects, 9 contact points with their associated contact forces, and an example of a friction cone in green. Then we dump these into a nonlinear model predictive controller, where at each control time step, we're using sequential quadratic programming to find the state input and contact force trajectories that minimize our distance to the goal over the time horizon, with some regularization terms in there, subject to the robot kinematics, the balancing constraints that we just discussed, collision avoidance constraints, and any state and input limits. So here's an example without those constraints. So in this case, if we want to move fast, we actually have the objects sliding or falling over, but in contrast, when we actually do enforce constraints, we can still move very quickly without dropping anything, and you see that this sort of intuitive tilting motion that still allows us to get pretty high accelerations naturally comes out of this optimal control formulation. And finally, as I mentioned before, so here's this example where I'm throwing a ball at the robot while it's balancing this tall pink bottle on a tray. So it has to both get out of the way, but not do so aggressively that the bottle is dropped. And that worked pretty well. Thank you very much. And that's the dream, but we're not quite there yet.
Cool. Hello, my name is Bennewitz. I'm presenting KinScene, model-based mobile manipulation of articulated scenes. This work was led by Changchun Su in collaboration with myself, Shenyu, Yuka, Roberto, and Joydeep. So interacting with articulated objects is a critical capability for mobile robots operating in human environments. For example, preparing a meal or unloading the dishwasher requires that the robot interact with several degrees of freedom in the scene. And these objects are going to vary in size and shape and appearance, and we need to build systems that are capable of addressing this challenge. So we formulated this problem as the goal of changing the scene to a desired kinematic state. So you have some start scene, some start configuration of the scene, and you want to interact with multiple degrees of freedom in that scene to achieve a goal configuration. And doing this requires that the robot reason about dependencies between the objects. So for example, in this case, the robot needs to open the dishwasher before it's able to access the drawer inside the dishwasher. And in this other example, opening the dishwasher blocks the robot's path to subsequent objects in the scene that it may need to interact with. So we need to account for all of the objects in the scene, their kinematics and their geometry, and really enable planning if we want to solve these long horizon articulated object interaction and ultimately task planning problems. So existing work focuses largely on individual articulated objects, either estimating their articulation properties with passive sensing or just attempting to interact with them in a zero-shot manner, just deploying a pre-trained model. And then task and motion planning typically assumes that we have access to a pre-built, accurate kinematic model of the entire scene. So in this paper, we're interested in building a system that's capable of integrating all of these components, sort of from the ground up, deploying a robot in a novel environment, building a kinematic model of all of the objects in the scene, ultimately enable task planning to solve these longer horizon tasks. So this is KinScene. KinScene consists of 3 stages. The first is a mapping stage, where the robot builds a 3D scan of the environment and a 2D map. It then goes around and discovers all of the articulated objects in the scene, essentially categorizing handles, pulling on them to interact with them, using that embodied data to build articulated object models. So recovering the geometry and the kinematics of all of the objects in the scene. And ultimately, this enables us to do planning. So determine a feasible sequence of object interactions that achieves the desired scene level configuration. So here's the robot exploring. It occasionally fails during exploration, but we have a sort of robust procedure for trial and error, interacting with all of these objects, takes that data, builds the articulated object models, and ultimately does planning. So at deployment time, it's able to interact with the objects more efficiently and more accurately. So we compared this to a random baseline that just interacts with objects at random to try to achieve the desired scene configuration, and we see that it's really necessary to reason about these different dependencies and model the object's geometry and kinematics if we want to actually solve these sorts of tasks. So this is KinScene. Please feel free to check out the code, come talk to us at the poster. Happy to take any questions that you have.
Thank you very much, all of you. Do we have time for maybe 1 or 2 questions to any of the spotlight papers? Okay.
Hi, my question's for the Act for MoMA paper. How does your system deal with failures, like a failure to execute a motion or it tries to grab something and falls, configuration of the system changes, how does it deal with those problems?
Thanks for the question. So there are certain failures that are recoverable and certain are not. For most failures that are, let's say, you couldn't find an IK solution or something like that, the only way forward is to just keep sampling more and more paths, and then eventually you get to a solution. The more tricky part is if the environment changes, essentially you need to start from scratch again because you've reconstructed the scene by sampling different RGBD images while you were moving, but now since the scene has changed, you can't use that old information anymore and you have to get it again. So essentially you just have to do the whole pipeline again. But this is something we have to find a way to build a scene representation that is more dynamic and interactive. But this is something that still needs to be done here.
I see, thank you.
All right, I think, and then also in the sake of time, we'll thank the speakers again. And our next speaker is Tetsuya Ogata-san, who's currently a director at the Institute of AI and Robotics at Waseda University, and in his current research is investigating human-robot interactions, dynamics of human-robot mutual adaptation, and intersensory translation in robot systems with neurodynamical models. So very excited to have you here.
Thank you. Just a moment.
Hello. Nice for the introduction. So now I'm Tetsuya Ogata from Waseda University Defense. So it's my pleasure to have this opportunity to talk here. So today I'd like to show some examples, demonstrations in our learning model based on deep learning, but actually it's inspired on findings from the neuroscience, brain science. Actually based in lies in the developmental robotics. And it's actually deep learning, so as you know, shows a very good performances for handling the image, sound, text, something like that. Now, everyone now interested in robotics applications. But as you already know, it's still very hard to apply the deep learning directly to the robot hardware. So what's the problem? Maybe it's related in problems that is called the Moravec paradox or something like that. But it's very important to considering this kind of paradox to consider new next AI, not just made a learning model with a big data. How can the real robot, real agent adapt to such a dynamical and open world? So again, now we need to consider about the use of the learning model. So actually, deep learning firstly applied to, for example, the robot vision or reinforcement learning. That is, of course, very important and very promising approach for the application of robotics. But both of approaches require a huge size of data because they are aiming to make the perfect model. From the viewpoint of the machine learning, of course, the training data to obtain the optimal model is always important, I know. So once the input the image and the recognition rate of the 98% or something like that, I understand. But of course, at the same time, from the control engineers, robot engineers, we know always we have some errors between the real world and the internal models. Right? In that cases, in the control systems, we always use some kind of control, like a feedback control, right? How to reduce the error between the model and the real world. That kind of sense could be applied to the use of the machine learning. So my approach is not for the learning model, inference process. How can we use such a learning model for the robot controls? So from the viewpoints on the behavior-based robotics, so this is a very, very kind of ultimate hypothesis. So we don't need learning. We don't need the representations. Just preparing the body and the environment, then some small size of the neural models. So as a result of the coupling between such a neural models, body and environments, some of the complex behavior could be generated, emerged as interactions. So that kind of concept could be enhanced by using deep learning technologies. So actually, considering the passing walking, so walking model with an oscillator, nonlinear oscillator, it of course works very well. In that case, but non-linear oscillator is very small neural networks, right? But now we have deep learnings. So this is one of the examples done by over 10 years ago by us. So completely end-to-end, from the pixel to the motions, handling the multiple object. We also follow what everyone calls the imitation learning balance. Here, the imitation learning means not just to imitate the trajectory. How can we replicate, how can we imitate the generative models to generate such a trajectory? So now everyone knows the generative AI, but actually 10 years ago there's no such kind of concept anyway. But so that kind of concept is very important. So again, it's back to the cognitive processes of humans. So now he seems to be a little bit confusing in front of the gap between his image and the real. So Earth models, but he expected to see this size and so US and American, South American size, but actually here is African EU. How can he reduce this prediction error in short time, in real time? So the time is also very important. In the case of the machine learning, there is no consideration about such time limitations. But as you are robotics researcher, we need to adapt such a kind of the gap very short time, right? So from the viewpoint of machine learning people, of course, we need to increase the data size, right? So we need, so of course, in Earth model, we can capture many images around the models. So by using an app or something like that, we can obtain the completely perfect 3D models of this target. I know, of course, it's important to increase the size of the learning model, but now is not time to train the model. In that case, there are two ways. One way is changing the internal cognitive state. If the target is just recognize the Earth model, such kind of the difference of geometry is not so important, right? Of course, if the goal is to finding some city in the Earth model, it becomes very big problems. But if handling the object, there's not so big problems. Or we can change the environment by generating the motions. And now then, he directly moved us. This is a very ultimate case. But it's okay, just make moving ahead to change the direction of the sea or something like this, or make the attention or something like this. That kind of the idea is always very important. So again, back to the sensors and behavior-based robotics, how can we consider the coupling of the body environment and neural dynamics? So here we made this kind of the models we now call deep predictive learning. So the learning model is designed as the dynamical systems. Here we use a recurrent neural networks, but any type of prediction model could be works. I still believe that recurrent networks so is important in the sense of it has some hidden state to keep the consistency of the self. But anyway, so now the target is proprioceptions and exteroception. So like vision, sound, and also the target is one body motions. Okay? And this prediction could be regarded as a kind of the actions. It could be changed in the environment under the body. Body also the target of the predictions. So there are always a gap between errors between the actual body and the environment dynamics and the neural dynamics. And based on this error, so using sometimes backpropagate, sometimes entrained the body and the neural dynamics. Then there are two. Of course, we could make them more hierarchical systems, but now we just show the two layers. One is lowest, that means fast dynamics. It's tried to entrain the dynamics in the sense of very fast dynamics. So it could be corresponding to, for example, torque control or something like this. But if the prediction error becomes large, so fast dynamics cannot adapt to it. It can be changed in one manner for more global senses. So here is slow dynamics predictors. It's so some restriction dynamics, so it can change very slowly. So that is so through the learning process, it's encoded to the combination of this kind of fast dynamics. So that means that this slow dynamics always makes some kind of goal or expectation for the long horizon time. This kind of the difference of the multi-time scale prediction. And between these dynamics, so small dynamics always try to adapt it, but it cannot sense, and the slow dynamics also could be changed. So goal state or trajectory could be changed. Okay, so now I show some example. This one was actually 8 years ago. So imitation learning manner, completing no models from the pixel to the motions. Here is the current state of this robot's target and following towers. And this is the prediction images. And this prediction is to feed back to the entrain the neural dynamics and the body and the environment. The environment here means in the towers. Right? And I put the towers in the untrained position. Actually, we collect the data only 50. So actually, the 35 should be enough, but 50 trained data. And so here we put the untrained positions. Then the prediction itself is not complete. Now you can see there are not clear boundary between the towers and desks. But it's okay. This is his cognitive state, something like this. So we human cannot see the real world as it is. We always modify the senses with our top-down predictions. So the same things happens for the motion generation. This is trajectory of the joint angle. And the dotted line is the training data, but now I put this untrained position, so that this motion should be changed to reduce the prediction error. So this one could be a kind of the predictive cognitive change, predictive coding, so how can we change the cognitive state? And this could be corresponding to the active inferences, and so change the motion to reduce the prediction error for the four cognitive states. So this is the result of 8 years ago and 6 years ago. And so this one is, we put this very roughly, but a robot promptly reacted to the tower's position and change of the shapes. So we collected 50 data with different types of towers and placed in a little bit different positions. But not whole requires the whole data, just putting randomly. This is untrained powers. But the robot promptly reacted to it. Now he imagines the towel, but which color is different from this? Because the towel's color is not target to the reducing error. The size is important. And here, so student found that this robot can hold a book. Of course, untrained object. And now robot imagines the towel, the same size of the towel. But no problems. Our cognitive state is also something like this, not always precise. With including some error, then with the predictions. Such kind of the manner is very important to the conducted real world interactions. So our technology is already applied to the many applications in the industrial robotics company in Japan. So this robot is working from the pixel to motion, directly training. And this is just a demonstration, but by changing the training data, this robot can conduct the different type of tasks, picking the salad, holding the towels, just changing the training data. And this is the target to measuring the powder. It's already used for the industrial company in line for the chemical experiments or the medicine or something like this, cosmetic also. And it's released 3 years ago as this kind of software in the Japanese industrial companies. we call the AI. Here is an imitation learning. Okay, here now I'd like to show the examples as much as possible. Time allows. This is so also the 6 years ago. Okay. Maybe someone sees imagines similar to the Aloha or something like this, but 6 years ago. Okay. So so target is opening door and passing it. So we show this demonstrations at GTC conference. So as you can see, the robot automatically approaches to the door so that we train the one prediction model to the approaching door. And now some of you notice the robot now starting moving the arm during the closing, approaching the door. So actually, we separately teach it, opening door and approaching door. But as a result of the competition with some prediction models for the opening door and approaching door, then during the approaching, the arm is automatically moving. This kind of combination happens. And this one is already published in Science Robotics 2 years ago, and it's selected to cover of this issue. So, so you can see that this shows very stable motions. And so, again, so not end effector is always an end effector works as an end effector. For example, in the case of this robot, vehicle parts is used for the opening door, keeping the okay. So whole body is always important, I feel. End effector, once we just focus on end effectors and motion or behavior is strictly limited. Whole body dynamics are always important. And so by interacting or sometimes helping, the robot can continue the motions. And these two doors is untrained door. Of course, the type of the door should be same, but some of the change of the color or something like this, that is not matters. And okay, I believe that I can talk no more. So this one is sorry written in Japanese, but the target is an opening zipper. Opening zipper is also very difficult. In the sense of the robot have to change its own trajectory during the opening the bags. So it's okay just keeping the same torque, just keeping the same trajectory. That is very easy. But so in this case, the robot have to adapt to the change of the shape. And you can see the robot now is a little bit confusing. That is a confusing motion is very important. So as replanning in the very short time. So now we train this robot only 36 motion data for the imitation learning. And this robot also uses tactile sensor in the fingertips. And the tactile sensing condition is also the target of the predictions. Then I cannot enough time to explain the detail here, but this is the attentional point. Attention is come from as a result of the prediction, not come from the image only. Always try to predict the motion, then this attentional point. Attentional point is strongly related not to sensory, but actual motions. Okay. That is very important. So thanks to attention, it can adapt to the change of the color, so drastically the color changes the background. And also, next scenario I like. So this target is an attention target given to by the sentence language. So I can talk about the integration with the language model, but this time I skip it. So, oh, sorry. Then here. So this is a real image, captured by image. And this is the image, so cognitive state of this robot. So now you can find, and so the target object is here now recognized. And the other object is completely disappeared, so ignore it. To generate this type of cognitive state, then this robot can continue to this works. The detail we use written in array data or something. So, 5 minutes, I'd like to explain this moonshot project. Quite a big project supported by Japanese government. And so it includes goal 1 to goal 9, and goal 1 and goal 3 related to AI and robotics. And our project now belongs to the goal 3, of which project director is Toshio Fukuda. He is the founder of the IROS and used to be the president of the IEEE. And our group and project manager is Shigeki Sugano. With the target is general purpose robot. Now many companies now interested in this target, but our project started in 2020. Yes, a little bit old. And so I believe that the robotics will follow the same way with the iPhone or smartphone. So it used to be the device, so different types of device, right? Of course, if compared to the performances, the smartphone is still not beyond each such a specific device, right? But once these functions packed to these devices, then it shows and generates new values beyond the summation of these devices, right? As a market, okay. And this one is now, so we need show the many robots, different types of robots, which goals different. But we hope this could be merged. And the case of the smartphones and iOS and Android is very important to change the function of these devices. And now I think that our AI technology could be play a role such kinds of functions to change the robot type. So we don't know the humanoid is the best shape for such kind of target. But Waseda University developed the first humanoid in the world, 1973, 50 years ago. So our interest is still keeping in the development of humanoid robots. And by using the changing training data, the robots shows different types of demonstration. This is a scenery exhibited at IROS 2022, 2 years ago, held in Kyoto. And this robot has an equipped torque sensor or all joint that become very soft. So this motion is used to such kind of function to keep the impedance the same. Then the ground cleaning is very easy to generate it. And the other 2 examples, for example, one is here, so cooking. So Saito-san sees and firstly proposed and so target of the scramble egg. So at that time I said it's okay, just randomly moving. But if we do so, the result is something like this, okay? Before the eating, very easy to judge, we cannot eat it, okay? So actually in this case, she taught this robot with grasping its arm and something like this, and started trials. And she cannot explain detail what she doing now. Because always it's very depends on the visually, on the tactile or something like this. But after training, the robot can cook it. So you can see the robot seems to be changes its motion strategy according to the X changes to its stiffness gradually, right? This is so acquired, so we can analyze the internal states of the recurrent neural networks, then which attention is first is mainly used in vision. But gradually, the cooking proceeds, the attention move to the more tactile senses. That is very interesting. And here is we already released an open source software now in April with an attention mechanism. So if you are interested in, please take the photo here. Okay. Thank you. And okay, and this ICRA. We'll show some demonstrations. Actually, placed here. So Moonshot booth and also Hitachi booth. So now the opening JIPA is a collaboration work with Hitachi. And now ask the Hitachi to join our project as a PI. And now you can imagine some of the demonstration. Actually, they will have to do it. But we'll show this kind of the demonstration not by video, live demonstration, not the video. Live demonstration is very important, I said twice. Okay. So please visit our site. Maybe the demonstration will start it tomorrow, I think. But yeah, I hope you will join us. Okay, that's all my talks. Thank you very much.
Thank you so much for the great talk. I think we have time for some questions. I would have one question maybe to start off. How far into the future are you able to make these predictions? Is this like, or at what frequency? As obviously everything diffuses into the future.
In this case, we're considering to the target and complete one task in the opening dependency in these cases and opening to something like this. So not so long horizon. So in the to complete the opening door and passings, and we combine the multiple prediction models for the approaching is and opening, and by using the mixture expert manner, so by comparing the prediction error of each modules, then the motion is combined. So by combining such kind of multiple module, we expect it shows some long horizon motion task.
Okay, thanks.
Thank you.
Yes, please.
Thanks for the nice presentation. I have a question regarding the learning in general. So you do the learning in a task space or in a joint space, or is there a compromise between the two?
Thank you. So in this case, all motion is trained in the joint spaces, joint space and the pixels, and sometimes tactile sensing. So now we basically use raw data. And then through the training phase, we expect some representation. Actually, today I skipped some explanation, but we can confirm that this lower layer or the higher layer could acquire some representation corresponding to the state of the task or more long horizon motion task or something like this. That's so because I'm come from the developmental robotics. I like the manner of the infant, how infant train runs in the world. So I always try to follow their manners.
Good evening. Thanks for the talk. My question is about the use of hierarchies, either like for temporal abstraction or like for hierarchies in modeling. You played with that also similar like to fast dynamics and slow dynamics. Have you considered like multiple levels of hierarchies in your work? Thanks.
Thank you. So in current implementation, basically we use just two hierarchies. It seems to be enough to the organizing the motion controls and some motion task representation. But as I experienced to enhance more long horizon task, we need to such considering the combination of such a layer, slower layer. So actually, of course, we can use another way to add a more slow layer there. So now those both approaches have the advantage and this pros and cons now we compared to the maybe some very reliable motion should be represented something like this, and by merging some of the skills we expected and it shows some new types of motion. Then the third layer might be well worked. So depends on what types of motion generation we expected.
Okay, thank you very much.
Thank you. Thank you for attending.
And with that, I would like to welcome our next speaker, Lydia Chalvatzaki, who is the Noah Harding Chair and Director of the Ken Kennedy Institute at Rice University. And in her research, she has not only shaped research, but also produced widely used open source software, such as the Open Motion Planning Library. And yeah, beyond that, doing research in biomedicine at the same time. Yeah, very much looking forward to your talk.
Okay, let's get started. Thank you very much for the invitation. I have found the workshop very, very interesting so far because it has exposed so many aspects of how it is, why it is so hard to do mobile manipulation. And actually, I've changed my talk a little bit since, as I was listening to others. I would like to talk about fast, robust motion planning, the work that is coming out of my group, especially during the last year, touch a little bit about task planning, and give you my thoughts on how we can achieve mobile manipulation and embodied intelligence. So it is clear that this audience is not interested in specific tasks. We are all aware that we can do very specific tasks amazingly well, even if this involves coordinated somersaults, and you've seen many examples. And the issue becomes, what is happening for robots for broader tasks? This is, I think, where most of the work is being done right now. Where are all the robots? Where are the robots in hospitals, in households, in construction? Do we want them to be autonomous? I would argue that we want them to be human-centered and collaborative. How do we get to this kind of behavior for mobile manipulation? The work in my group shows that we need long horizon task and motion planning, and we need that to be efficient, robust, and safe. How do we get there? You've heard, and I think it is clear from the talks in this and the papers in this conference, that there are many ways to approach this problem. One is by scaling up, and we have evidence of what has happened when we scaled up large language models. Going from GPT-3 that had 175 billion parameters to Gemini that has billions of parameters, we don't know how many. The tasks that can be performed are more and more impressive. And there is no doubt that we've seen similar work in robotics, and we had a talk this morning from Google DeepMind. One recent paper, AutoRT, combines large language models and visual language models and a robot control model, and it is very interesting to see what is the result of this work. Let me point out from the paper that they used 20 robots simultaneously, up to 52 unique robots in total, in a variety of office buildings, gathering a diverse data set comprising of 77,000 robotic trials across 6,000-something unique tasks. It is impressive what is happening, and the data is scaling up, as you saw this morning from the talk. And it's definitely interesting, very much interesting to see where this will get us. I don't know where this will get us, but definitely what we would know today is that this work needs a lot of time, a lot of energy, and a lot of money for it to become successful. We are only scratching the surface, because even if these models are successful, what happens about safety, explainability, transparency, bias, what happens about human collaborations, which are all, I think, attributes that we would like to see from our robots. So it is actually an open question, I think, in the community, how to go about mobile manipulation and how to solve this problem, maybe with a combination of approaches. Maybe this is where the answer lies. In our group, what we are doing is a combination of classical methods and learning. And this is what I would like to focus on in the rest of the talk, and that's why I gave you this introduction. The way we approach the problem is we concentrate our efforts on developing core capabilities, and motion planning is a core capability for robotics, in our opinion, exploiting modularity for long horizon planning, and putting the human in the loop. There is no way that in the next 20 minutes I'm going to talk to you about all these efforts. So what I'm going to do is I'm going to concentrate on the first one, develop core capabilities, motion planning, and tell you about work that is coming up, that is happening in my group, especially during the last year. And this work will be presented this week at ICRA. And I'll say a few things about exploiting modularity for long horizon planning and putting the human in the loop. Very little. So let me get started with developing core capabilities motion planning.
I don't need to explain motion planning to this audience, but I just want to say that the tasks that we want to solve are becoming more complex, and we want efficiency and we want safety from our planners. I'm talking about the classical motion planning problem, and those of you who know a little bit about my history, I've been in this working on this problem for a long time now. So this is the case shown here in a very simple example. We solve the problem in the configuration space. The space is implicitly constructed given the geometry of the workspace and the geometry and kinematics of the robot. And when we have a free path in that space, we know that we have a free path in our configuration space. All the approaches that work on motion planning never construct the obstacles. I mean, actually, it's impossible to construct the obstacles in a very high dimensional configuration space. If you would permit me, I would roughly, let's say, put the different motion planning that we see today under these 5 categories: sampling-based motion planning, which is the work that has been definitely a work that we have started and contributed a lot to; heuristic and discrete search approaches, optimization-based approaches, control theoretic approaches, and learning-based approaches. As far as sampling-based approaches are concerned, just a very, very quick recap. What is happening here is that a tree or a different kind of data structure is built in the configuration space of the robot by exploring, that is generating configurations and joining these configurations until you reach the goal. At this point, you have a path. This is the classical RRT algorithm, and there are many, many versions of it. For example, the successful RRT Connect will start both from the start and the goal, and try to connect these two trees in the middle. And there are other kinds of data structures that capture the connectivity of the space, for example, roadmap-based planners like PRM. A lot of work has happened on this domain, and if you are working on sampling-based motion planning and you need a planner, my advice would be not to start writing one from scratch. We are distributing the OMPL library, which is an open source library that implements all the planners that you see in this slide. It has been tested by many. Actually, we estimate more than 3,500 users of this library. We have a number of unique visitors in our web pages, and this library is available in many package managers for all common operating systems. So visit that library and also visit the kind of tools that we are distributing through our lab if you want to work on sampling-based motion planning and you need a good starting point. Initially, when I received the invitation for this workshop, I was going to talk to you about multimodal planning. But now I'm going to reduce this to a few slides and talk to you about very, very fast motion planning that we can do. Multimodal planning is the work of Zhang Kingston at Rice University. This is the case where you need the robot to move on a manifold, on a constraint manifold. As you can see here, the tip of this robot moving in this ellipse. There are many ways of solving the problem, but the way that Zach solved this problem was to endow the space, the configuration space, with the basic operations that are used by sampling-based motion planners, and then any kind of planner that from the ones that I showed you before can be adapted to the problem at hand. Here you see Robonaut 2, a NASA robot with 34 degrees of freedom, doing a whole body motion, sliding a door or turning a valve, and these are problems that are solved with the same framework. And once you have this framework, you know how to move in a manifold constraint. But if this manifold constraint intersects with another one, you can jump to the other manifold, and then you can obtain a very complex behavior, which I call multimodal planning. So the robot here does a whole body motion, as you can see, and moves from one mode, the mode is holding a handrail, to another mode, holding another handrail, going from one end of this space capsule to the other by doing this multimodal planning and moving from one mode to another mode in an automatic way. For more details, I will refer you to the paper, which is at the bottom of this slide and was published at Transactions last year. Let me move on to something that I find extremely exciting, and this is a paper that will be presented at ICRA at the Motion and Path Planning session, which is on Wednesday afternoon. This is work of Will Thomason and Zach Kingston, and it's motion planning in microseconds via vectorized sampling-based planner. Let me preface this by saying that the summary of this work is that we can deliver kilohertz planning. This is done with a CPU, on a CPU, using single instruction, multiple data parallelism, and intelligent collision checking. Our planner VAMP that you can see on the left on these slides, on this slide, will solve the problem that I will show you in a fraction, in 0.42 milliseconds, while the same problem with OMPL and PyBullet takes 46 milliseconds to solve. So it's an impressive boost in the performance of the planner, and we've noticed this, planning times consistently. You may tell me that, well, I'm very happy with 46 milliseconds for solving this problem. Why bother? Well, you need to bother because if you have ultra-fast motion planning, then you can put the motion planner inside the control loop. So look at this video. I will let it play so that you can digest it. In this case, we are obstructing the motion of the robot with the cylinder, and the robot dodges the obstacles and adapts to a changing environment. This is, I have not sped up this video. This is 1x. This is exactly as we see it in practice. Notice the smooth motion of the robot. Notice how quickly it adapts. And this is what you can get if you have planning, which is really, really, really fast, kilohertz rate. It is at the frame of the camera. Okay, so I'm really excited about this development because I think it's going to change the way we look at motion planning, the way we look at mobile manipulation, what we can do and what we cannot do. Motion planning is hard because we have high-dimensional search, we have, as I told you, the implicitly defined valid state space, and we have expensive operations to execute, like the nearest neighbor search, the forward kinematics, and the collision checking. And we are not the first who are parallelizing motion planning. Actually, there has been a lot of work in the past, starting in 1991. But all these works do what we call coarse grain parallelization. That is parallelization of routines that generate, let's say, threads in the execution of the planner. What we do is that we blend the naturally sequential and the naturally parallel operations of the planner at a fine-grained level. The main work is done at the forward kinematics and the collision checking part of the planner. And it is there because, as those of you who have used sampling-based planners know, that this is where all the time is spent, in collision checking. So in a nutshell, we accelerate sampling-based motion planning by, one, using a SIMD-friendly robot model, so a single instruction, multiple data friendly model. This is a kind of a sphericized model of the robot where we have covered the robot tightly with spheres. This is not new work. We used existing literature from graphics. The second thing that we did is that we produced hyper-specialized code. This means that we have a kinematics compiler that takes into account the kinematic tree of the robot and compiles down to assembly code that is optimized by a compiler. So it is really the best you could possibly do on your computer. And then we use fine-grained parallelism within operations. I will explain what I mean by that. And we schedule computation to avoid wasted work. So very, very carefully looking at the operations of a sampling-based motion planner. All these are done with the aim of exiting computations on invalid states as early as possible and exploiting the now ubiquitous CPU parallelism for low overhead and power use. Please, I want to emphasize here that we're using a conventional CPU and not a GPU processor, right? So something that we all have. The first two, 1 and 2, are done only once. That is the kinematic, the SIMD friendly robot model, and the kinematic compiler need to be done written only once. The other two are the 3 and 4 are the algorithmic improvements that we have achieved with the planner. I will not focus on 1 and 2. I will say a few things about 3 and 4, but really in order to get the details, we need to get to the talk on Wednesday afternoon to where we will be presenting this paper. So we know that when we when we execute motions, we have to do collision checking, and what is the best way to do collision checking in parallel. Typically, what we do is some kind of sequential collision checking, which actually wastes effort. So we'll check the green, and then we'll check the orange, and then we'll check the blue, and then we'll check the pink configuration. This is fine, and there are variations of that, but the way that we do things now is with what we call direct collision checking. All 4 of these configurations will be checked in parallel using single instruction multiple data parallelism. So if one of them fails, we know that we cannot execute this particular path. But if they all succeed, then we know that we can move on and check at a finer resolution and a finer resolution until we are happy with the resolution that we've checked our paths and we have a safe path for our robot. And in expectation, we've seen that this really gains a lot of time. And the other thing is how to avoid wasted computation. For example, as you can see here, if the red link collides with the obstacle, I mean, why would we go and do kinematics for the tip of the robot, let's say? I mean, it's clearly something that we are not going to need. So we've managed to automatically interleave forward kinematics and the collision checking code. And the result of this is that collision checking is done as soon as possible, and the exit is done whenever possible. This is a combination and in combination with the SIMD parallelism, this can save a lot of time, as we show with our experiments. Our results, these are several cases from the robot benchmaker. It is a benchmark set that we have created and many have used in the community. It has a fairly difficult motion planning problems. Look at the running times. I hope this is not obscuring the running times. They are, the mean is 0.29 milliseconds, for example. I think I'm going to play this once more, if I manage to, okay? So look at the planning times and look at the kind of problems that we are solving. The mean, medium, and 95th percentile are shown here, and the planning times are really, really fast. So we are very happy with this kind of performance. I mean, I, at some point, never expected to see that, and I think it opens lots of ways of rethinking what is the role of motion planning in robotics. We have done extensive comparisons that you will find in the paper, especially our baselines are OMPL with PyBullet and MOVEit. OMPL is our motion planning library that I discussed at the beginning. MOVEit, I hope you all know it, the motion planning framework underpinned by OMPL, and the PyBullet, the popular physics simulator for robotics. And the data set is our motion benchmaker. I will not show a lot of results, but this is the Panda robot. In orange, you can see MOVEit with OMPL. In green, you can see PyBullet with OMPL. The planning time is the x-axis, and these are different planning problems. So the distribution of times for our framework is order of magnitude lower and clearly separated by the other approaches. This doesn't happen all the time, but it is a very consistent behavior what we are seeing. The thing that I need to say, however, here is that the lengths of the paths that we are producing are very similar to what we had before, and this is what I tried to show you with the plot on the right. An important issue here is that because it's just a CPU and it's not using any heavy architecture and heavy processor, this approach can work on a low power hardware, for example, on an Orange Pi. The results that you see in this table are hard to read, but VAMP, which is our approach, is in the enclosed purple rectangles, and it is running on the orange Pi. These are in seconds, what you can see, the running times. The Pi bullet, however, and move it with OMPL are running on the CPU. On a CPU, they are not running on the orange Pi. So it is a performance that is interesting, very, very interesting, at least in the kinds of architecture that we are using. The approach is not only constrained to RRT, but it is constrained, it is applicable to geometric versions of sampling-based motion planners. So for example, now we can construct a 5,000 node PRM in just 5 milliseconds. There are catches, of course, okay? There's no free lunch. And the catch here is that we assume known geometric primitives in our space. And this is something that, of course, we knew it was a restriction from the very beginning. So there has been recent work in our group by Clayton Ramsey, Will Thomason, and Zach Kingston to alleviate this concern. And we are very happy to report that this concern can be alleviated. And in fact, you can have the behavior that I showed to you from planning from point clouds. And this is very interesting because this is how most of robots will get the environment and the changes in the environment. This was presented, a part of this work was presented already at the Agile Robotics workshop, which is happening concurrently with this workshop. The idea here is that we have SIMD-friendly collision checking, and because we have spherized robots, the collision checking can be done via nearest neighbors queries, plus adding the radius of the largest sphere of our robots. This means that we need to support these queries with nearest neighbor data structures. The ones that exist right now, like KD3s, will not do the trick because they are very hard to parallelize due to backtracking. And this latest work introduces a data structure that we call the collision affording point tree. I will not give you the details. I will just tell you that the collision affording point tree is the pink and the brown lines here. And you can see that he has a superior performance compared to Octomap or FLAN or other data structures that we've used for collision checking. And this is how we got the video that I showed to you at the beginning. The environment is changing. There is a single RealSense camera on the top of this environment that captures the changes in the environment. And look at the robot. It is adapting to the changes in the environment in real time. This video has not been sped up. So here, for example, it avoids this stack of cubes, and we change the position, it avoids the stack again. And I will forward to the end of the video, which shows you again this motion, the robot avoiding the stack. But if we, and I think it is at this point, if we change the stack, then the robot takes the short route. Okay. The takeaways from here is that motion planning can be done orders of magnitude faster than the previous state of the art on a singlet CPU and from point clouds. The key insight is the use of fine-grained parallelism with SIMD hardware acceleration to exit early from collision checking, and planning in microsecond. This is, I think, a game changer towards a deeper integration of planning and control, accelerating applications in planning. I will say now very few things about two other papers that we have in this conference, dealing with sensing uncertainty, which is going to be presented Tuesday at the afternoon section, work of Quintero Pena, Will Thomason, and Zach Kingston. And you know, point clouds, that we have sensing uncertainty. Sensing uncertainty has been dealt with chance constraints in the past. Producing safe paths is something that we are all interested in and we care about. The chance constraint, which is here at this box, guarantees that the points on the trajectory are going to satisfy user-specified risk tolerance. These are hard to model, environment dependent, and expensive to evaluate, this chance constraint. So the work that we are presenting learns an implicit neural representation to quantify the uncertainty of sign distance between the links and points in space. So we not only learn the distance, but we learn a distribution for each link of the robot. And having this distribution, we can create a hierarchical chance-constrained planner. We use a motion planner to get a path, which may be a risky path, and then we use our neural representation to repair, let's say, this path hierarchically, first the first point and the first link, the first, let's say, segment, and then the second segment, and so on and so forth. And this is a chance-constrained inverse kinematic solver that that will be presented tomorrow. The results are safe paths. Here is an example. The red path is the originally computed path. Well, it's not safe. It is very, very close to obstacles due to uncertainty in sensing. The result is the brown path that you see here. And if I zoom in, you'll see that in parts of the path that were close to the obstacles, we make this correction to minimize the risk of having a collision. The takeaway here is training an implicit distance model can work very well, and splitting the problem into a learned sensor model and an algorithmic planner gives us guarantees and generality without having modeling assumptions. This is not a fast planner, but we are working on it. Now, let me finish this talk by telling you that we are very much interested about long horizon planning and how to explore modularity in that, and also how to put human in the loop. Regarding long horizon planning, I would encourage you to go to the talk of Ken Elimelech, which is on Thursday, the 16th of May in the morning. And he is going to talk about accelerating long horizon planning with affordance directed dynamic grounding of abstract strategies. It's a mouthful, but what is happening here is that he has a way to extract strategies which are generalizable experiences. These are stored in an abstract space, and this space is mapped to the space of the robot when it is needed. The paper operationalizes these abstract strategies. So if, for example, your robot has seen how to do a tower arrangement, it should be very quickly and efficiently do this same arrangement in a similar way, even if you have distracting objects. And if you have multiple towers, no matter how many you have, it should, again, work very efficiently. And putting human in the loop, I think sometimes we forget about it. I will play a video that shows a human and a robot working together. The human is interfering with the task, sometimes not in a productive way, but the robot finds a way to complete the task. How can we get this kind of behavior fast, reliable, and with performance guarantees? I think it is an issue that is very worthwhile working on. So this is what we are working on in my group, developing core capabilities for motion planning, understanding how to do long horizon planning in a cheap way, and putting the human in the loop. At this point, I would like to thank the collaborators, my students, and I made a particular mention to the authors of the corresponding papers, and especially the ones who will be presenting at ICRA. And thank you very much for your attention. And by the way, we are hiring. If you are interested in these topics, please write to me. Thank you very much.
Thank you so much. Very impressive work. Do we have any questions? We have time for maybe one or two.
Hi, thank you for the great talk. One of the things you mentioned on the side was putting the sampling-based planner inside the control loop of the robot, right? Now, one of the problems why people tend not to do that is because of planned commitment changes, for example, like planned commitment changes, for example, like the first sampling plan deciding to go left, and then the second one on the second update just going right, or just violating velocity constraints, basically dynamics constraints. So how do you handle that there? Is there some guarantee that you will stay with the current first part of your trajectory, or?
Okay, this is a very complex issue. I think it's not something that you can easily do. In all the work that we worked on, we looked at the geometric case, right? And in that case, because we looked at the geometric case and because we were so fast, we were able to show you the smooth behavior that you saw in the videos. Now, if you have very, very fast changes and dynamic constraints, it's to be determined if you can do that or not. But it's done so fast that I think you probably can keep some sort of memory and manage to achieve something which is reasonable. I will stop here. Will Thomason, who is one of the authors of this work, I think wants to tell you something more about your question. Thank you.
Okay. I think then we will
okay.
Stay on track. Thank you so much.
Thank you.
Our next speaker is Chen Chung, who is a professor at Queensland University, where she is focusing on perception, planning, and learning for robotic mobile manipulation, as well as navigating through crowds and informative path planning.
And I need to also share my screen, is that correct? Okay, I think I've got everything set up. Wonderful. Thank you very much, and thanks for inviting me to give a talk at this workshop today. So my name's Chen Chung. I'm from the University of Queensland, as was introduced earlier. And what I'd like to talk to you today, or at least convince you today about, is the need to keep models. Because I think right now we're in a state where we like to learn everything, but I think there's some very useful information that we still have access to, like the geometry of objects and understanding where and what objects are. And we also have models of our own platforms that I think we shouldn't discard when we think about mobile manipulation tasks in particular. So my talk is about reasoning about these things, reasoning about the objects that we want to interact with and the agents that we're using to do that interaction. And I want to actually just start off by acknowledging some very important people here, because I'm the one up here speaking to you today about this work, but it does come from the minds of many, many people that I've been able to collaborate with over the past. I'm from the University of Queensland now, but previous to that I was working at ETH Zurich in the Autonomous Systems Lab, and I still collaborate very closely with the people there. And so the work that I'm going to speak to you today about are from students and the brilliant minds from both of these groups, both at ASL and my lab at the University of Queensland. So if you've seen any of my talks in the past couple of years, we do like to show this example of how we've learned to do grasping using volumetric representations. So this is work by Michelle Breyer, who you see up on the screen, where given just a depth sensor where we can get access to geometric information about the scene, we can encode that in something like a truncated sine distance field, and then we can pass that through some kind of a black box to come out on the other side with some information about where we can place the gripper in order to successfully grasp something. And so we want to use all the information that we have available to us from our sensors. We know the geometry of the scene. We know where the surfaces are. So we know, for example, that there's no point trying to grasp in empty space, which is further away from a surface than the depth of the fingers. All this information is extremely valuable and should be used inside any tool that you have that's trying to interact with the physical world. And so of all of these things that we know about the environment, we want to bring all these ideas into the solutions that we have. And so this is what we came up with, the volumetric grasp network, where we can scan the scene, understand where the surfaces are of this environment, understand through many interactions, through simulation training, data that we can gather very quickly and offline, and then be able to transfer that into the real world, where we have a sensor, scenes, objects inside our scene that we've never seen before, but still just with an understanding of the geometry of what's in front of the robot, be able to propose grasp poses in which will allow us to actually interact with the scene successfully, in this case, meaning to grasp that object. Now, in this case, what we're looking at was just the grasp. Could we actually synthesize successful grasps? But one thing you'll notice is that in order to do that, we first had to scan the full scene. And that was one of the longest components of this work in the execution time, was actually scanning the whole scene. And for us, if we're trying to get our robots into our environments to do useful tasks, usually those tasks are not just grasp everything that's in front of your robot. We're usually wanting it to grasp something specific. And so if you know what it is that you want the robot to interact with, then we should use that information. And so if we're looking at grasping, in this example, the box of orange cookies that are sitting on the table in front of the robot, from its current viewpoint, this is what the robot is seeing. So it sees a very small component of that box, and it can use that single frame, that single depth image, to already propose where it might be able to grasp different objects in the scene. But because we're specifically interested in grasping a specific object, then the geometric information that we have of that target object isn't sufficient at the moment. So rather than just scanning everywhere, we should think about where we should place that camera so that we can get the best view of the target so that we can successfully complete the task. So if in this case we were to move the camera to a different viewpoint, for example, if we were to look at the scene from above, then we would get a different view. We would understand more about the geometry of the scene, and we would understand more about the geometry in a way that would allow the robot, the agent, to actually become more successful at proposing a good grasp. So in this case now we have a much clearer view of a part of the target object that is no longer occluded by other objects, and we can propose a better grasp that is more likely to be successful. So the way that we wanted to incorporate this geometric information was thinking about this representation that we have, which is this truncated signed distance field, and understanding how, when we pass this through our grasp synthesis algorithm, how we can, first of all, segment out the grasps that are the ones that are on our target object, but then also consider whether or not these grasps that we've proposed are sufficient. Because if they are, why bother keep looking? You know, you already know how to grasp the object, so just go ahead and do it. You don't have to waste any more time scanning the scene. But if that's not the case, if we don't have enough information, then we want to think about where we should actually be placing that camera to be able to achieve this global task. So now we're looking at the segment of our 3D scene, where the object we think should lie. Where are those voxels that we can't actually see, and where should we place the camera to reveal the most of that scene that will actually allow us to become more efficient at our task? So being able to hypothesize this by looking at the geometry of the scene is exactly what Michelle did in this work, and allows us to therefore have a closed loop grasping solution. So now we have active perception. Rather than just scanning everywhere, we're only placing the camera in locations which will allow us to reveal parts of the scene that are relevant for the particular grasping task that we care about. And so when we compare this to other baseline methods, for example, if you were to just look at the scene from above, and in many cases this is actually quite a good viewpoint to look at things, because generally even if you have piles of objects, they're usually fairly singulated when you look at it from above. But then there are, of course, going to be limitations. For example, when you have the Tupperware, where the robot can actually grasp the object is necessarily from the side. The finger widths are not wide enough in order to grasp from the top. And so in that case, looking from the top is not sufficient. An algorithm which takes all of the geometry of the scene into account is able to then propose a new viewpoint that will allow it to see the rim of that bowl in order to then be able to grasp the object. So now this work was assuming that you had an initial view of the target object. So you had some idea of where the thing was that you were trying to interact with. And so the next natural question to ask is what happens if you have no idea about the object that you're looking for? So you don't know where it is, you don't know what it is that you want it to interact with. So if I were to tell you that the task for this robot is to find and grasp or retrieve a small cube inside this scene, where would you say, given what you can see right now, where would you say the cube would actually be? Are there any suggestions? Yeah, it's under the cup. I mean, for us, it seems extremely natural. Like, you've looked everywhere. It's not visible. If someone tells you there's definitely something in there, the only logical place it could be left is underneath the cup. It's hidden. And so no amount of looking is ever going to be able to reveal a part of that target object. Now you actually have to go and interact with it. You have to go and interact with the scene, lift up the cup to actually go and find out where that is. And so that indeed is what we need to do. So now we're combining not just the camera viewpoint selection, but we're also bringing the grasp capabilities back into the task of retrieval. So not only is grasping suitable for retrieving the object, it's also suitable for revealing new parts of the scene that we couldn't see before. And it doesn't just have to be fully obscured, like in the case where it's completely covered, but in the case where there's large objects in the way, sometimes you can try and look, but potentially it's more efficient to just move the thing out of the way and then see more of the scene in that sense. So the question, of course, is then, when should you grasp? What's the effort balance in terms of placing your camera somewhere to see something versus trying to actually go and physically interact with the scene? And it can be kind of a tricky question to ask because you don't know how good your robot is at grasping things, you don't know how good your perception is at being able to reconstruct your scene. And so when it comes to these kinds of questions where you know, for example, that in this scene here, now potentially we're looking for a rubber duck. The small rubber duck that we can't see currently in this first viewpoint, but we do know how large it is. We have some idea of its volume, and we do also have some idea about what parts of the scene we cannot see, what we do not know, what we know we do not know. And so with these two pieces of information, we can already begin to hypothesize about where our target object could be hiding. And in that sense, we can then start to consider, well, is it going to be faster to go and place our sensor to go and look at those hidden locations? Or is it going to be better to try and remove an object from the scene to reveal those hidden locations? And there's obviously going to be a trade-off because the amount of time it takes to do one thing or another and the probability of success of doing one of those or the other is also going to be different. Generally, if you want to move your camera to see something, you're very likely to succeed. If you're grasping, however, there can be the chance that you attempt to do a grasp, but then that fails and you interact with the scene in a way that you did not actually intend. So to balance between these two things, Tom Pitcher, who was the student working on this, proposed to actually try and solve this using reinforcement learning and formulated a reward function that would try and balance these two actions against one another. So there's a few kind of tricks that we needed to include here because there's a few structural changes when you're comparing the value of a view versus the value of a grasp. First of all, the number of views that you might have, you can fix that. And when you have something that's fixed in size, it makes it something very easy to learn because the structure of your network can be fixed in size as well. But the grasp options, these are ones that just come out of our grasp synthesizer. So for different scenes, you're going to have a different number of proposed grasps. You don't want to be considering grasps that are not going to be successful. And so in that case, we can't rely on having a fixed size input into our network, or at least we can't treat them all together in the same way. And in this sense, what Tom decided to do was actually to consider both of these actions slightly differently, to have a view agent that he would evaluate and a grasp agent. Both of these agents need to know something about the geometry of the scene. So again, we pass through the truncated signed distance function encoded in some way as the state input for both of these agents. We also want to pass in some information about what the robot itself is doing at the time when it's making this decision, because where that end effector is will change how long it's going to take to be able to successfully move the camera to a certain viewpoint or indeed to go and grasp at a particular location. So having that information is also quite valuable in understanding how efficient that action is going to be and how successful it might be. And then the final thing we want to pass in is each of the individual view actions or grasp actions one by one, and we can evaluate them sequentially as they come in. We can evaluate these things in batch, so it can be extremely fast to do these. They don't have to happen in serial as you're seeing them here. But what this allows us to do is then take into account potentially varying numbers of grasps that might be available that come out of our grasp synthesis algorithm. So again, we compare, this time we're actually comparing against our own VGN network. So VGN, in this case, does not consider grasping or viewing for a particular object. It was simply going to view the scene and grasp whatever it thinks it can grasp. And the target case here is to grasp this green object, which we see down the bottom in the foreground for us, but actually hidden behind this white block in the scene. So when we look at these two in comparison, this is running in real time. The first thing that you notice is that the active search algorithm that Tom proposes is quite targeted. It looks for objects that are hiding things and tries to get them out of the way. VGN, however, will grasp whatever it thinks is most likely to give it a successful grasp. In this case, it happens to be one of the tall blocks on the right-hand side. And as it's doing that, we already see that the active search algorithm has already found where our target object is, because after it's taken that block away, it's trying to place the camera in the best location to reveal more of that scene that is just disturbed. Whereas for VGN, what we hard-coded was to allow the robot to move the camera right back up to the top so that it has the best chance of seeing everything inside that scene. And unfortunately, in this case, of course, I picked the case where ours looks the best, but VGN itself, it doesn't actually do so poorly, because once it does find the target object, it will indeed go and try and extract it. So far, we've looked a lot at just grasping alone and how we can take into account the geometry of the scene and all of the knowledge that we have about how the robot interacts with that scene to improve the way that the agent is going to interact with those objects. Now, of course, this is a mobile manipulation workshop, so I want to also bring in some mobility components to this. And I want to show you some examples of not just grasping, but whole body interactions with articulated objects. So this work is done by Giuseppe, who you see on the screen here. I'm just going to skip to the work that he's done, where we are looking at how we can incorporate additional safety constraints to understand not only how the robot should place its end effector and interact physically with different objects in the scene, but also how that we can guarantee passivity, how we can guarantee that the amount of energy that the robot injects into the scene is managed so that we don't have kind of catastrophic events happening. Now, the target task in this case is to open the door completely, but us tricky folks, roboticists, we've placed a rope in the way so that it's actually blocked. And you'll see that even though the robot is trying to achieve this task, because the rope is in the way, it tries to keep injecting energy into the system until it reaches the threshold that we've actually set. So you see that threshold being reached, and it doesn't exceed that. So even though it's still applying a force, it's not accelerating anymore. And so once we go in and cut the rope, the robot's actually able to recover. It doesn't fly off out in the other direction, and it's able to actually successfully complete the task and also safely complete the task. So these kinds of interactions are a bit more complex because we have a lot of changes in dynamics from moving in free space to moving in contact. And when we do this kind of whole body manipulation, we cannot neglect to understand the agent that's actually doing the interaction. We need the model of the agent in the system in order to compute all of these components. So inside what's happening in here, there's a lot of rollouts that are happening in the back end, and those rollouts all depend on understanding the kinematics and dynamics of the robot, the agent that's actually interacting with the scene. So what you've seen here is how we can open a door. Now, one thing that I want to note is when we were executing this, where the robot places its finger was something that we fixed at the beginning. And so that was one of the limitations that we wanted to address, because it doesn't matter where the robot places its finger, we just wanted the door to be open. And if the door is slightly ajar, there's really no need for the robot to use the handle. It can place its finger anywhere along the open door and continue to push to successfully open that object. So in that sense, we wanted to extend some of the work that we've seen out there to understand where to interact with different types of articulated objects so that we didn't have to manually specify this ourselves. Now, there's work out there, for example, the Where to Act papers, as well as the VATMART papers, which were already starting to explore this back in 2021 and 2022. But as we were looking into this, our first response was that we wanted to try it ourselves, but we noticed that there were some things that were a little bit difficult for us to actually transfer into our system. And the first one being that a lot of the results that they were showing, a lot of the methodology that they used, did not include the full model of the robot. In these examples here, you see that here they are really just simulating the gripper, just where the hand is meant to go. So it's flying around, and the way that they generate these point clouds, so these heat maps that you see on the surfaces, they spawn the hand in a particular location and they apply a certain trajectory onto it, and whether or not that trajectory is successful is then labeled. But there are some kind of strange things. For example, in some of these drawer cases, in order to open the drawer, they spawn the hand inside the drawer when the drawer is closed, which seems a bit odd because if you have a mobile manipulator, that's not really something you can actually do. You've got the whole rest of the robot to also deal with, not just the hand. And so given that we really do understand the robots that we're working with, and generally we have models for them, we thought it would be such a shame to not consider them as part of our solution. So this is exactly what Paula and Giulio, who you see on the screen, worked with. So they brought in the sampling-based controller that you saw demonstrated from Giuseppe's work a few slides ago, and they wanted to bring that whole model, the whole sampling-based controller, into the learning framework, so that when we have our perception module come back and say, look, this is the part of the object that I want you to interact with, we understand that the agent that's doing the interaction is going to have some influence on the success of that interaction itself. If you give me a different robot, it needs to interact with an object in a different way, depending on its kinematics, the way that it's set up, its reach, its workspace, its configuration space. All of these things are going to factor into how you actually want that agent to interact with that object. And so bringing that model into our system gives us what we call agent-aware affordance understanding. And so when we compare, for example, our results to what was the state of the art at the time, we can see that the heat maps that we generate in terms of where we think the robot should interact with a particular part of an articulated object begin to make a little bit more sense knowing that we have a mobile manipulator. So even though this door goes all the way around, the heat map applies largely up on this top right corner because that's the most reachable part of the door, right? Rather than also saying, okay, stick your hand underneath the door and try and open it from there, which doesn't make a lot of sense. Understanding that the agent that you're trying to interact with these objects has its own set of limitations allows you to really narrow down and focus your solution so that you have the best shot at actually having a successful interaction. So that's for the opening task. For the closing task, it's something similar as well. And you can see here in action. So these are, again, scenes and objects that were not available to the robot during training, but we always have the model running in the back end. So we can always forward roll out, forward propagate what we think the outcome of the scenario is going to be and bake that directly into our affordance understanding. So in this case, we're looking at opening tasks. We don't consider dexterous manipulation. A lot of what you'll see here is really just with a single finger, a single rigid point contact. But what you'll notice is that it doesn't require that particular contact point to stay in the same location. It can slide across the object. There's nothing that stops it from doing that. And in this example here, in the real world example of it trying to open this oven door, in particular what you'll see is that it will change its contact point. So as it comes in for its first interaction, it decides, okay, somewhere up the top seems like a good idea to first make contact and try to open this door. But after it starts to interact with this object, at some point it realizes that it's not making any more progress. It can continue to observe that even though it may try to continue opening this door in its current configuration and at that current contact point, it's not the best place for it. So it takes a step back, looks at the scene again, decides based off of what's going on in the object space and also understanding its own model, now where should it be interacting with the object in order to successfully complete the task. So bringing that in, the whole loop in, I think gives us this edge because we understand not just what objects we want to interact with, but also the agents that are doing that interaction. So an extension of that, moving on, is not only do we want to think about interaction at a single point, but also interaction at an object level. So what we know from a lot of computer vision work out there is we can do a lot of segmentation. For example, if I were to show you this kind of scene, we can very easily label different parts of this scene as chairs, tables, and so on. And even for some of the more advanced methods out there these days, if we have objects that we may not have human labels for, we still might be able to hypothesize what these things could be. And I think what we would like to do from that sense is not just to understand what these things are in the environment, but also how an agent could interact with them. And that's where we would like to extend this kind of semantic knowledge that we currently have to also bring affordances into it. So this is work by Paula and Antonia. They're looking specifically at how we can try and build up data sets, how we can try and send our agents into the world to not just collect data about what things are, but also how those agents can interact with those objects. Because no matter how much you spend time looking at a chair, you don't really know that you can actually sit on it until you sit on it. And once you sit on it and you successfully stay sitting on it, then you know forever that you can sit on that chair. And we want to bake that kind of knowledge into our agents as well. So what we have access to are things like objects, instance level maps, and we also have agents that can go out into the real world or in simulators like this, like iGibson that you see here, to actually go and interact with those objects. So you can push them, try to pick them up, and in that way actually have an understanding of how that agent and object can actually interact. Where we can build up these kinds of data sets, there's two ways that we can do this. First of all, by actual interaction. And so the objects that the agent interacts with will generally be interacting at a single point, but we can, with the semantic segmentation information that we have, apply that across the entire object if we know that it's a rigid object. So even though we may have only tried to push the couch in this specific location, we can actually apply that affordance knowledge to everything that we observe as being part of that couch. The second way that we can collect data is by looking at our propositions. So what our affordance network actually comes out and says, okay, I think we've seen us being able to successfully interact with lots of different types of couches before. So I see another couch in the environment. Therefore, my confidence is fairly high that given that it's the same class, roughly the same size, that these are the kinds of objects that I can also interact with in the same way. So we can apply that knowledge and kind of extend or extrapolate to other things that we may not have physically interacted with, but we can already start to propose ways that we could interact with those objects, and then use that information then to retrain our affordance networks. So this is work that's currently under review, so you're getting to see a preview of this. And here we're showing you some results on the iGibson dataset, where we've driven our robot through this environment, learned about the different types of interactions that the robot can do with the different objects that are in the scene. And we're trying to show you here the affordance predictions that our solutions are coming up with. And the goal here is to have as much white and green on the screen as you like, and less red and purple in this case. So white and green being the true positive and the true negative labels. So you see that with the semantic map knowledge, so not just treating every single frame as something that's completely new, not treating every single chair as being something new, we're able to learn much more about how our agent and our objects interact with one another and extrapolate that information across the whole scene. So to wrap up, the thought that I want to leave you with is, we've worked a lot with semantic segmentation, semantic understanding of scenes, but I think as we go into mobile manipulation really out in the wild, out in the real world, I think we need to move beyond semantics, and instead of just labeling things as what they are, we need to bring in ideas of what are those agents that we actually want to put in that environment to interact with it, and think about how these agents can actually interact with their scene. So rather than just saying, look, this is a chair or this is a table, but as objects which are pushable or sittable or pick-upable or placeable, and having representations that can capture that information will allow us to do much more efficient planning and have much broader and much more tangible understanding of the scenes and what we can have as interactions in those scenes. All right, so thank you very much. I want to, again, bring up my collaborators and thank all my funding sponsors, and I'd be happy to take any questions that you have.
Thank you so much for the great talk. And yeah, I think we have time for one or two questions.
Yeah, thank you very much for the wonderful talk. So I agree that models are actually crucial and important. And the last part or the last slide of your talk about affordances is also fantastic. Do you have an idea which models actually can be used for affordances? Or how would you include knowledge, model knowledge about affordances into all your work?
Yeah, that's a great question. I think, I don't know, this might be a bit old-fashioned now, although at the pace at which we go, what isn't old-fashioned? That wasn't done 6 months ago. But for a while, I think we were using a lot of neural radiance fields for doing reconstruction, or not reconstruction, but rendering. But the promise of NeRFs and neural radiance fields was not just that they could make you a picture of the scene from a point that you hadn't seen before, but that they could capture feature information about the scene in a way that wasn't just the geometry or the color, but actually any feature that you had a label for, you should be able to also train, so long as you had the color and depth information too. So for a while, this was some of the work that, which I didn't talk about today, but some of my other students were looking at how do we use NeRFs to actually have more generic feature fields, not just to be able to render volumes or render images, but potentially to render other feature fields that come out of it. And that other feature fields could be affordances. I think we've seen some examples of people using NeRFs for doing semantic segmentation. They're very, aligned tasks when it comes to being able to do 3D multi-view geometry. But the challenge with affordances or anything in the space where we're actually looking at the agent and the object interacting is that you need labeled data. And that's extremely challenging and extremely expensive. So there's obviously work that's happening in the space of simulation, which I'm rather excited about. I think there's a lot of work now coming out of big groups that have a lot of resources that are trying to make our 3D physics simulators much more powerful and much more reflective of the real world. So I think we could potentially leverage some of that to generate more synthetic data to begin with. But at the end of the day, like you say, if you don't know whether or not you can pick something up, the best way to figure out if you can do it is to go and try. And once you can pick it up, you know that to be true. So being able to put that information into a representation where it's not probabilistic anymore, but actually, yeah, I picked it up. It's definitely true that I can pick it up and not be at the whim of something that could come back and you infer on it the next day and with some new training, it's forgotten that knowledge. I think that's going to be extremely challenging, but I think there's a few ideas out there that we're floating around.
Yeah, thank you so much. I think we'll just stay on time, but thank you very much. And with that, we have another set of spotlight talks. And yeah, you do offer the first paper. Did you have sound? I don't know. It's previous person. Yeah. You just stop sharing. Should I connect the Gmail? Yes, please. A second. Is everything good? Okay. We can make it smaller. It's here. The first screen, just to see nice. I'm sorry. No worries. I don't know what happened. The last worst case we can also do the public recording and so it's trying to find the recording. So I can just do it without Zoom, that's fine. Okay.
Hi everyone, I'm Kushal from Cornell University. Hello, it's good? Okay, I'm just going to start. Okay. Hi everyone, I'm Kushal from Cornell University presenting Mosaic, a modular system for collaborative cooking with multiple robots. Let's just get started seeing the robots in action. The robots communicate with the user in natural language. They decide the task to perform and the recipe to make. You can see here the fixed base manipulator is picking up the salt to pour into the pot, the human is cutting vegetables, and the mobile manipulator goes to fetch the soup base from the shelf. What's interesting to note here is that all of these skills are being run by machine learning models in real time in the background. What even further, the human position is monitored through an overhead camera, and we predict the future human motion through a motion forecasting model. As you can see here, when the human hand comes in, the robot doesn't blindly just keep stirring the pot, it stops and makes way for the human. There are some key challenges that we are trying to tackle in different modules. The first, that we want the task planner to interact with users in natural language. So we pass in the conversation history into a large language model and use a behavior tree structure to guide the conversation towards task completion. Then the large language model assigns tasks with appropriate object prompts to each of the robots in the scene. And then the challenge becomes that we want to perform these skills across a range of everyday objects. For this purpose, we first pass in the object prompt. In this case, kosher salt. The mobile manipulator has to go and fetch this. We use a vision language model to extract the object pose, and this object pose is is passed into an RL policy to produce final robot actions. The last challenge is that we want the system to seamlessly and fluidly collaborate with humans. Certain skills, such as the one in the previous slide where you are stirring pot, has very close proximity interactions with the user. In these scenarios, we detect the current human pose, we extract the 3D coordinates of its history, pass it through a motion forecasting module, and then this motion forecast can be used by the robot to update its plan. In this specific scenario, if the motion forecasts come very close to the pot, the robot stops stirring, makes way for the human, and avoids collision. This brings me to some key features of our system, the first being safety. In real time, we have a pose detector, a media pipe, which is running all the time, detecting the human pose, a motion forecaster that predicts the future motion, and based on these motion forecasts, the robot responds to the human coming into the scene. The second key feature I want to highlight is recoverability. In this scenario, the robot was going towards the ketchup, but the user changes their mind, they want soup base instead, and then the vision language model changes its target, and the robot picks up the correct object in the scene. We evaluated our system end-to-end across a variety of recipes, specifically 6 different recipes, each of them run 10 times with a human user in the loop. That brings me to a brief talk about the system. I'm happy to answer questions either here or in the poster session after this spotlight.
Thank you. I think we'll take questions after all spotlights, so maybe the next offer can just, but stay around in the front.
I messaged media. Got it. Is it? Hello, everyone. I'm Karmesh Yadav, and today I'm going to talk about our recent work titled Embodied EQA, Embodied Question Answering in the Era of Foundation Models. We present a novel formulation for embodied question answering, in which the task is about understanding environments well enough to answer questions in natural language. We propose 2 subtasks in embodied question answering. The first one is episodic memory embodied question answering, in which the agent is given a video of it exploring in the house, and it is asked a question about the video. And it needs to look at the video it was provided and answer in natural language. Another subtask that we propose is called active embodied question answering, in which the agent is randomly initialized in the house. It is given a question, and it needs to explore the house to find the answer to the question. So for example, to find if the microwave was open, the agent would want to go towards the kitchen, look at the microwave, and find the state of the microwave door. So in this case, the answer would be no. Based on these 2 tasks, we propose an evaluation benchmark called OpenEQA, in which the questions are answered using open vocabulary text. The benchmark contains around 1,600 non-templated question answering pairs, which are created from around 180 plus videos from real scans of environments from ScanNet and HM3D scenes. And the benchmark supports both the task that I was showing previously, and we propose an evaluation metric to evaluate the answers to the questions. Based on the provided subtask, there are multiple categories of question answering pairs. For example, questions related to object recognition, attribute recognition, object state recognition, etc. The distribution of the different categories of questions is pretty much uniform across the questions. If you look at the distribution between the 2 scenes, we have more questions from ScanNet compared to HM3D. And if you look at the distribution based on the subtype of task, we have around 1,600 questions from EMEQA and 557 answers from active EQA. One of the biggest challenges of evaluating open vocabulary answers is that there could be multiple possible answers for a particular question. So we propose a metric called LLM match that looks at all the possible answers to the question, and along with it looks at the answer that the agent gives and scores the answer from 1 to 5. And if you look at the Spearman correlation between the performance of a human and this LLM-based evaluator, it's more than 90%. Then we look at some baselines. So we first start with a human evaluator, and we get a performance of around 85%. Then we start with a simple baseline with a blind agent, which is just provided the question and it needs to answer based on that. And it achieves around 30 to 40% based on the LLM being used. We also come up with a baseline where we're using a recently proposed approach called concept graphs. And we integrate concept graphs with the LLM, where the LLM is supposed to give the answer to the question. And it actually achieves performance very similar to the blind agents. Another possible baseline is when you're using a frame captioner, which gives captions for all the frames, and then LLM looks at the captions and answers the questions based on that. And this agent achieves somewhat better performance compared to blind agents. Finally, we also use multimodal LLM, specifically GPT-4 Vision, and that achieves much better performance on the task, but it still is lagging behind human by around 35%. In summary, we proposed the first open vocabulary benchmark for embodied question answering. We propose an automatic evaluation metric that has high correlation with human judgment. And finally, the benchmark is challenging for the current generation of foundation models, and there remains a lot of work that we can do in this area. This work was done at Meta along with my amazing collaborators, and thank you so much for listening to my talk.
All right, good afternoon, everybody. My name is Owen Lemke. I am currently a master's student at ETH, and I'm also the main author of Spot Compose. Now, I can already hear you asking, what is Spot Compose? So Spot Compose is really a framework that we built for other computer vision researchers to basically do modular implementation of modern vision techniques on a robotic framework. So in this case, we actually use Spot. If you don't know what Spot is, that's this little guy right here. And the idea, so why do we do this, right? The idea was really quite simple. There's a lot of modern research, right? There's 2D models, there's 3D models, there's open vocabulary models, there's a lot of other models. So what can they actually do sort of in practice, right? Can we actually use them on a robot? Are they good enough to use on a robot? So for this, we look at 2 different tasks. Number 1 is object retrieval. Object retrieval, really, you just give a natural language query for an object. Spot has to look for that object and then retrieve it. And on the other hand, draw manipulation, so that is finding all the different draws in a scene and then looking through them and finding a certain object, which we describe with natural language as well. So for both of these methods, we actually start with the same thing. So the first one is scene reconstruction. So the idea really is just you have a scan from the scene, which you just use a commercial scanner, in this case an iPhone, and then you do 3D instant segmentation. In this case, we use OpenMask 3D to do that segmentation. And then from there, it basically just looks like this, right? So this is the segmentation we have. Then we look for the water bottle, and we isolate that object. And then we use another model, in this case, any grasp, to then look for different grasps. And then we can see Spot executing that grasp. And we here have a joint planner between both the position and the grasp, such that we can align them, right? You can think, in this case, the water bottle. If you want to grab it from that side, you don't want to stay on the other side and then grab it like this. You want to grab it from that side. And you can see that works quite well. On the other hand, if you want to do draw manipulation, we can't really rely just on the 3D features, right? So in this case, we actually use the 3D features to look for the cabinet, but then we can actually use just the camera in the robot to look for the different drawers and the handles. And once we have them open, we can then simply open them up and then look for any object inside. In this case, we use MOMA.v2 to basically do open set object detection. And really, you can see that the framework, really the idea is that it's very modular, right? So you can combine a lot of different modern vision techniques to then get a working robot out of it. So for the results, you can see for the object retrieval, we get about a 51% success rate, which is comparable to other modern results. We tried on 6 different scenes and 13 distinct objects, ranging from very easy, like plushy toys, to very hard, like watering cans. And then for the driver manipulation, we actually get an 82% success rate. So here we see we have about 100 trial runs with 15 different handles. Some of them, again, quite easy, but some of them hard enough that even I might have problems grasping them. So the takeaway is really, if you're a computer vision researcher, if you don't have a lot of experience with robotics, then this could be for you. If you want to sort of validate your models in practice, maybe even develop in practice, then this model is very modular. It allows you to integrate your modern techniques, and then it streamlines development. So for me, the first 3 months to implement grasping took about 3 months, and then the draws only took about 5 days. So yeah, thank you for your attention, and if you have any questions, then feel free to come to the poster session.
So thank you very much, all offers. I think since we are a little bit behind, we will skip the questions for the spotlights, but all the offers will now be available at the posters as well, so you can directly ask the questions to them there. And yeah, with that, we will have posters and coffee until 4 o'clock. Please make sure to vote for the best poster. I will put up the code in 1 second. We need your vote, very important. And yeah, see you soon for the next presentation. Okay, everyone. I think we will continue. So the posters are very exciting, but I think we just want to make sure that everyone makes it to the welcome reception in time. So for our next speaker, I'm very happy to welcome Tamim Asfour. He is currently the chair of the Humanoid Robotics System and head of the High Performance Humanoid Technologies Lab at the KIT. And he's been tremendously impactful over a long time across both soft and hardware landscape, in particular of humanoid robotics, developing very innovative designs such as the ARMA robot family. So we are really happy to have him here, talk about humanoids and mobile manipulation.
Yeah, thank you very much for inviting me. There is an echo, right? So, and now? Okay. Yeah, thanks a lot for inviting me to talk at this workshop with such important topic. I think this is the goal of many of us, to have robots not only grasping and manipulating objects, but which is still a very challenging and difficult task, but to move around actually and to perform manipulation tasks. And we as humans, we are actually, So we as humans, actually, we perform these mobile manipulation tasks in a very efficient and very intuitive way. We can select, or we have to select in these tasks, object placements in order to achieve a certain goal. We know about the reachable space and what are potential placements for objects. And we automatically and intuitively actually select the right arm in order to execute a task, select the right grasp, and maybe also respect some social norms in mobile manipulation tasks, as you see here in these examples. How it is in robotics, I'm sorry to use this video which is sped up by 20 times, but to show you what I think that mobile manipulation should be. It should be the ability of robots to grasp any object in any environment, like household environment, but more maybe industrial or decontamination task environment here, select grasps, to move around, and to place these objects at the goal in the goal position. So, and this was exciting today. Several talks actually address several aspects of mobile manipulation. One could say, okay, mobile manipulation is the perfect coordination between navigation and manipulation, where we need a lot of motion planning, what Lydia, for example, showed us in her presentation. Mobile manipulation is also the question about how and where to place objects. Of course, this involves object grasping. So as you see, object grasping and object placement is for me a part of a mobile manipulation task, and both of them, in particular grasping, is still a challenging problem. But mobile manipulation can be also done in an efficient way if we plan actually. We know what are the actions which should be executed on an object before grasping this object and manipulating it, as I will show soon. And for me, mobile manipulation a few years ago, when I started actually thinking about it, it's a problem of active perception. Is the problem of a robot moving around all the time, and it has to find locations of objects, to update knowledge about the scene with its moving sensors. This is what people were doing all the time in active perception, where actually the parameters of the perception system are changing and where we have to deal with these challenges. You see here some examples actually of work we did a few years ago on how to localize objects during motion. Yeah, for example, here, of course, only the torso motion of the robot is used in order to simulate disturbances, for example, and where you have to stabilize images in order to grasp these objects and to manipulate them. And on the other video, which you cannot see or you saw already, actually, is about how to use visual information in order to do vision-based grasping while moving. This may be the definition of mobile manipulation. You grab objects and you move and you manipulate them while moving. So as mentioned, I'm working on humanoid robotics since more than 20 years, and these are some of the robots which you will see in my presentation. So we focus mainly on household robotics actually, but with applications also in other areas. And here you see some of the tasks what these robots can do since 17 years. The ARMA 3 is 17 years old and it's still functional and can perform all these tasks, not in this old kitchen, but also in a new kitchen actually, which we have now. And now we move to a new building where we will have another new kitchen and where the robot should be able actually to transfer all this knowledge to a new environment. But also more complex things like setting up the tables for two people, which involve a lot of mobile manipulation tasks. It's not only about the sensory motor control here, but it's about the mapping of this natural language instruction like, Amma, please help me to prepare dinner for two people, into actions, into robot actions. And this is before the area of generative AI and large language models and all these things. So where the robot has to understand actually what are the abilities which it can perform and which tasks should be performed by the human, like cutting the salad, for example. It should understand that setting up the table requires two chairs, 2 plates, 2 cups, and so on. And as you see here, the robot is able to perform these mobile manipulation tasks with complex grasping and with complex activities actually in general, while also reasoning about functionalities of objects. For example, here, replacing the salad bowl by the mixing bowl based on visual affordances, or replacing the Coke by a multivitamin juice based on tables we extracted from data mining in 2017, and we use in order, for example, to offer Katya here a multivitamin juice instead of Coke because we don't have Coke at home. So many of these capabilities are transferred currently to other areas. You see here the area of repair and maintenance tasks, where the 6th generation of our robot here is supposed to provide help to technician in repair and maintenance tasks. This means actually to recognize what's missing in the current situation. For example, a second technician who is supposed to be there to help in lowering this heavy guard, or to recognize that the human would like to hand over an object to the robot, or to carry this guard and to place it in a certain location in the warehouse environment, and so on, or to set up the ladder, for example, in order to do the inspection of these guards here. So these are a wide variety. I think I don't need to say that all of them are mobile manipulation tasks, which require maybe a perfect coordination between navigation and manipulation. We have not been working, actually, we're not working on navigation per se and SLAM. We are taking state-of-the-art methods. We are focusing in our research only on grasping and manipulation, but both of them are needed. Another example where we are using these robots is the decontamination of nuclear facilities or installations, and you see how these tasks are performed these days. The human in the yellow suit is the person who has to grasp these contaminated objects, of course fully protected according to German regulations, and to place these contaminated objects on a rotating table, to clean it, and then to grasp it again and to place it in a clean box. And this is what we are trying to do. What we are trying to do is actually to solve this task by our humanoid robot. And these are very complex environments. The objects are unknown in advance, so you have actually to find ways how to grasp and manipulate these objects in these unstructured environment where you have little or no knowledge actually about the objects, and we rely very much on the concept of affordances, where we defined a very simple set of rules actually with which we can, based on the visual information of the scene and extracted geometric primitives in the scene, can detect which areas are graspable, pushable, which areas are liftable, and so on in the scene. These are all these hypotheses are based on geometric information and are, of course, subject to validation through physical interaction with them. And what we did here, you see here an example how these extracted hypotheses, grasping hypotheses in these cases, are generated and selected either manually by human sitting actually and selecting the next grasp which is proposed by our affordance system, or by a human with VR, AR techniques, wearing these head-mounted cameras and selecting the right grasp, or where the execution is happening completely autonomous, and where we showed actually that the error rate can be reduced in grasping, so the success rate can be increased in the case of grasping objects here, when you, of course, put the human in the loop, yeah, in the semi-autonomous mode. What I mentioned before, grasping or decontamination tasks means generate grasping hypothesis based on visual information of the scene, grasp the objects, place them on this rotating table in order to clean them, and after cleaning them, you have to grasp them again, actually, in order to put them in the other box. And you see here some of the work we did in the last years where we grasp the objects, we place them on the table. Of course, everything here in our lab, not in a decontamination cell of nuclear plants. And then we grasp them again by generating a new model while exploiting different views or multiple views on the object in order to grasp it and to place it somewhere else. So, and in mobile manipulation, what's maybe important is actually the fact how can we combine navigation and manipulation in efficient ways so that we can execute tasks in a faster way. Here, a work which we presented at IROS 2022 on combining navigation and manipulation costs for time-efficient placement of the robot in mobile manipulation tasks. And as you see, the execution of a mobile manipulation tasks means actually a whole body, the generation of a whole body motion of the arms, of the hand, of the torso, and of the mobile base in the case of a humanoid robot. And you see here the placement, the first placement of the object, R1, and of course, again, for the second placement, another whole body motion must be generated, and then the second placement, R2. And what time-efficient execution means actually minimization of the time required to execute all these tasks. This means the tasks to move from the initial position to the first placement position, the time needed for the generation of a whole body motion, the time needed to move from the placement position R1 to the, for example, subsequent placement position R2. And in order to do that, we actually, in order to minimize the time, we define a cost function which we minimize, which describes for us both the manipulation and the navigation costs. And in particular, the navigation costs from the initial position to the first robot placement position where the object should be grasped. And then the manipulation, which of course should consider dynamically distance to obstacles, and the costs which are needed for the manipulation. For example, consider the manipulability index of Yoshikawa, which we extended in order to consider also joint limits and also distances between different parts of the body. And the navigation to the final position, and not only to one single position, but from this first placement of the robot to all possible placements of the robots at R2. You see here an example or an evaluation of this, what I presented here, where of course based on, of course the objects are given, known to the robot in this case, and we know what's the next placement position, and what the system is able to do is able to select actually the right arm in order to grasp the object, because now grasping this object with the left arm is more suitable for placing it on the next table. And as you see, grasping now the next object with the right arm is more suitable to place it on the table on the right. And by doing that, you can execute these tasks in a more time-efficient way, as I described before. If you are interested in the details, I refer here to our IROS 22 publication. So now you are wondering actually a little bit about what I talked about: kitchen tasks, about decontamination tasks, about repair and maintenance tasks. And this has been a very challenging thing also for us, with a lot of experience actually on taking software from one robot and from one environment and transferring it to another environment. And this has been now one central research question of a European project, a network actually of excellence, the EU Robin project, where we are addressing the question of transferability between different robots, different tasks, and different environments. And as we know from the definition of transfer learning in the machine learning community, transfer learning means actually improving the performance of robot A executing task A in an environment DA by taking advantage of knowledge from the source robot and the source environment and the original task. And as you see here, in this paper, which is under review in collaboration with people from EPFL, from Joseph Stephan Institute, and from KTH, that we distinguish between different ways of transfer, or we say that the transfer actually, we should consider transfer across different tasks. For example, the task in the kitchen and the task, the repair and maintenance task in a warehouse environment, or the decontamination task. Of course, between different robots with different environments, and between different environments, like the decontaminated environment for cleaning objects and the household task. And in this paper, we distinguish actually also between different levels for transfer. So the transfer should consider different levels of abstractions. If you talk about cognitive abilities, for example, of course you have to consider the entire hierarchy from mimicking actions, where you only execute the motor actions without thinking about what's the goal of the task, to imitation, where of course the goal of the task is very, very important. So goal-directed imitation or the goal is very important, and emulation, where only the goal is given, but you don't care about copying the motor actions actually of the agent, up to the causal understanding, where goal of the task and the motion are also given. So, and you see that we have to consider actually the different levels of abstraction, and what we are interested in now, or I'm going to talk about in the remaining time here, how we can actually transfer robot skills in the capability stack here, where you see we start with low-level joint controllers, go up to robot skills defined in the task space or joint space of the robot, up to task and motion planning, and then understanding of the fundamental understanding of the world on the highest level. And we do that actually to show or to demonstrate this transfer of robot skills between different tasks, robots, and environments on mobile manipulation tasks. And this is why we developed Makeable. So it's a framework for mobile manipulation, was submitted actually to this conference, but it was rejected, the paper. So thanks for the opportunity to present it here at the workshop. But yeah, I agree also with the reviews that the paper, the way how it was written and maybe how it was justified was not good enough for ICRA. This is fine. I'm not criticizing the review process. No, really very, very fair reviews, yeah. But I think we can contribute with this framework to the area of mobile manipulation. So it's a memory-centered and affordance-based task execution framework for transferable mobile manipulation skills. You see here our robot, the ARMA 6 robot. We have a copy of the robot, but with different kinematics. Is not exactly the same kinematic. For example, the hand has more degrees of freedom, and the hip, and all these things. And the tasks, like kitchen tasks or decontamination tasks, as I mentioned before, and of course the different environments. So what's behind Makeable? So, of course, on our robots, we have a complex cognitive architecture. And in this architecture, of course, we distinguish between high-level capabilities and low-level sensory motor skills of the robots. And for bridging these two gaps, we are following an approach where we think that in between high-level capabilities and low-level capabilities, a memory system should be there, which store all the information about tasks, about humans, about human skills, robot skills, embodiment, prior knowledge of about the world, about the robots, etc. So this middle level is very, very important for the skill transfer. And what we need in order to be able to take our Makeable actually to run it on your robot, we need representations which are suitable for mobile manipulation, representation which are suitable for transfer in general, but in this particular case for mobile manipulation. And of course, the fact that we are generating actions or action hypotheses based on affordances makes the representation we are using inherently transferable between different embodiments and between different environments. And the fact that we rely on memory-centered architectures allow us to accumulate the entire experience of the robots during the execution and to use this experience in order to solve new tasks in new environments. So how it is built, as you see here, very abstract representation, high-level skills, and the low-level control, and in between, this memory system where we distinguish, of course, between working memory, long-term memory, procedural memory, and episodic memories. And the execution of a task related to mobile manipulation, like grasp known object or grasp unknown object, is actually structured in five steps. So as I mentioned, the memory system is mediator between the two levels. And as you see here in this mobile manipulation pipeline, we distinguish between the discovery step, the parameterization step, discovery, which is about actually what are action possibilities. Of course, if the objects are known, you know immediately how to grasp them, but we would like to provide something which can deal also with familiar objects and with unknown objects. So this is why the discovery, the parameterization means actually, since these affordance-based representations are independent of the agent first, we have to do the mapping to the agent. For example, the mapping of the action to different robot hands or to different robot kinematics. Then checking for reachability and for feasibility actually of the action for a given robot embodiment. And since all these affordances so far are generated based on geometric information about the scene, we have to validate all these hypotheses through physical interaction with the world and then execute that in the real world. So, of course, the experience from in every step, in the discovery step, in the parameterization step, in the execution, and so on, is stored always in the memory and can be used to further improvements. And the transfer between the ARMA6 robot and the ARMA-DE robot, in this case, is happening via the information we gained or we stored in the intermediate as affordance-based representation in the memory. So again, the 5 steps of the pipeline: discovery, parameterization, so extraction of action hypothesis. An action is instantiated and parameterized for a specific robot or robot part. All actions are validated and checked, for example, for reachability, collisions, and whatever. And the best action is then selected for execution, for example, in an autonomous way or in a semi-autonomous way. And then, of course, the actions are executed on the robot. And the decoupling here, as I mentioned before, and the affordance-based representation of actions in general allow actually for this transferability between the different robots. You see here some examples. The 2 robots, the green one is the ARMA6 and the green-white, the ARMA-DE, performing actually with the same code these tasks, what you see here, like grasping known objects in household-like environments, or like grasping unknown objects where you have to generate hypotheses based, for example, on affordances, or placing objects, or as you see here, bimanual manipulation tasks in the decontamination area. For clearing the table example here, which involve a lot of grasping and mobile manipulation tasks, as you see here, we did this comparison with the set of objects, known and unknown objects, as you see here on the table, where the robot is able, of course, to select automatically the strategy to grasp known objects if the object is identified as a known object, or start the exploration in order to understand what kind of grasping affordances on this unknown part in the scene are feasible, and try these hypotheses and execute them. It's not only, also the pipeline and the code allow you to work actually with different sensor setups. So for example, you can switch between stereo-based 6D pose object localization for known objects, or RGBD-based visual perception of the scene. You don't need to re-implement again the different parts in order to execute something on your robot. We showed also that we can, with the same code, actually execute or transfer skills between these 2 robots. You see here, these are some skills which are taught to the ARMA6 robot by kinesthetic teaching. and where the skills are executed then by the AMA-DE robot. And you see also that the skill was taught to AMA-6 actually to open the door with the right hand, while the AMA-DE robot here is able to open the door with the left hand. And the most important thing is actually that the same code is running on both robots. So the code will be available. There is a project webpage, and we will release the code soon. We did a lot of modifications after the rejection of the ICRA paper, but soon the paper will be released and made available for all of you, hoping that it will be beneficial for your research. We developed a new household robot. This is the next generation of our robot, the AMA-7 robot. And of course, these mobile manipulation tasks, what I showed and demonstrated, will be then transferred to the robot, which has again a different embodiment. Yeah, maybe the same environment here, like kitchen environment, but a different embodiment in order to also show the transferability or how transferable the framework is. Yeah, with that, I would like to conclude. Thank, of course, my team, and thank our funding agencies for their support of our research. And of course, thank you for your attention.
Thank you very much for that presentation. I think we can take one or two questions.
Tami, I always have questions for you. The first one is about the memory mechanism. You mentioned memory several times. Is just an aggregation of past sensory motor experiences, or do you extract something and summarize into a different
yeah. Not really. When I say memory, it's not just a place to store things, but it's an active component in the architecture. So all processes which are needed, for example, to transfer something from the working memory into episodic or long-term memory, or to forget something in the episodic memory, are part of the implementation of the memory. So it's an active component with all services, actually, which are needed in order to manage the huge amount of data what you have in these examples. For example, our robot generate about 300 gigabytes of data every hour if you just store the raw data. And the memory, or part of the memory, are actually all services or all methods which allow you to, for example, build latent representation of the data and store the important things, or services which tell you that some of the information is redundant and you can throw it away from the long-term memory, for example.
And a quick second question about the transferability between embodiments. Your robots are different, but the capabilities seem to be somewhat related. Would that generalize, for example, to robots with a parallel jaw gripper? Is that something?
Yeah, this is actually independent of the gripper, because the actions are represented really on this abstract level, like grasp, pick, place, and so on. Of course, in this implementation, you have to provide the mappings to different robots. If you learn these tasks from human, for example, and you would like to transfer a task from human demonstration to an arm with 2 fingers, you have to do the mapping from a 5-finger hand to your finger. But all these mappings are there in the literature, you know? I mean, if people are interested to implement everything, then I think many people, they will not waste a lot of time in re-implementing things again and again. But the current conceptual structure and first implementation of the pipeline of the makeable allow you actually to do all these things. We don't have a mapping from, for example, our robot hand to a 2-finger gripper, but this is something, a known problem which can be implemented, yeah.
Yeah, thank you very much. Yeah, let's thank Tamim again for the talk. And then you can just stay on stage, and I would like to ask the presenters from the afternoon to join us on the stage again for a panel discussion.
You still want to add more, right?
Yeah, but which computer are we using?
I think this one. Not this one. See it? Okay, perfect. Perfect.
Okay, thanks for sticking around. This is going to be the panel session 2, and my name is Avinav. I'm a professor at the University of Freiburg, also a co-chair of the TC on robot learning. So we again have the Slido link, so if you'd like to ask your own questions during the progress of this panel discussion, please feel free to enter them here. We will also discuss some of the questions that we already have. So, all right, so let's start. So we have seen that today that mobile manipulation requires integration of a large number of components from sensing, manipulation, locomotion, and as well as the algorithmic capabilities that come with this. And this also comes with its own problems, right? Like synchronization, integration of various components to achieve the tasks finally. So the question is, how can we effectively integrate these different components? Do we keep the models, make them more modular as a differentiable pipeline, or just go end-to-end from pixels to actions? I think this is like a never-ending debate. So yeah, let's see. Start with Tetsuya, as you have the mic, or I mean, currently, I guess modular differentiable is winning on the.
Yeah, I know. Actually, so, as I talked in my talk, I take manner from the pixel to the actions. But at the same time, I directly emphasize the case of the human development process is that 3 months years of infants, then our brain is not so such a structured modularity. So even any type of sense in the all brain activated. But through the experiences, such kind of modularization emerged, self-organized. So of course, we need such a modularities and functionalities in the brain as a last. But from the beginning, maybe the end-to-end manner could be the first approach to obtain the functionalities. That is, so I always follow the manner of the humans. So that is my answer.
Any other thoughts of the panelists?
Yeah, I mean, I agree, but I think I think we need a combination of both. Yeah. So because I mean we know a little bit about robots. You know, we can maybe program, implement these innate skills what humans learn at the beginning of their life. We don't know how. And why should we waste our time in learning things which we studied in a very good way, actually, in robotics? I mean, we can implement reflexes, we can implement kinematics, we can do motion planning. And maybe on top of that, try to put advanced learning mechanisms, how we can improve models of the robots, model of reasoning about the world based on data.
I think that's also the trend that we're seeing, right? Like, I think the pixels to action is kind of very small, but more combination is what we see that works in the real world in diverse applications. So, yeah, any Jensen, if you...
Okay. Well, I agree with Tamin. I think we need both. I mean, what we know how to do very well, and I think it was very clear from my talk where I stand, what we can do very well, what we have studied, and I think we should do it with whatever it requires, models, or, you know, we should not forget the math that we have developed for so many years for kinematics, dynamics, control. I don't think we should learn that. We understand these models, we should use them. The key, in my opinion, is how we are going to take these models and make them part of, you know, learning systems, and also on top of that, take advantage of the capabilities of learning, which we all need to acknowledge are very, very significant. Now, how to do that, nobody knows. I mean, nobody knows the answer. And I do see parallels in other domains. For example, take scientific machine learning. They're not trying to reinvent the wheel. I mean, what are they trying to do? They are trying to take the physics laws and put them in the machine learning framework, right? This is how they are gaining big, right? This is where all the progress has been, not learning the laws from the beginning. Why I think a similar approach, I mean, as an idea, in robotics will take us much further than working only with models or working only with learning.
The one thing that I want to add to that is that if we go for the end-to-end strategy, what we lose is the ability to peek in and see what's happening, because then you have something that's relatively brittle. So if it fails, you don't know where it failed, what went wrong, which part of it you need to fix. So having modularity gives you that by the nature of the way that it's put together. So I think as engineers, it's useful for us to understand what part of the pipeline is the bit that needs more work. And so if we were to kind of remove everything out and just try and learn it from pixels to actions, I think we lose a bit of that.
Absolutely. I think I also have another question on that later, but let's see. We have another question, which I think is very interesting, also relates to some of the talks that we had today. So scale is all you need. Do you think that is the case? I think this is not specific to mobile manipulation, also can be general to manipulation. But in this case, do you think it's useful for mobile manipulation if the approach that we take of collecting large amounts of data, trying to get to, let's say, robotic foundation models, that's beyond manipulation here? Yeah, what are your thoughts? Elusive bit is leading 64%.
All right, maybe I start. I feel like when we first got into deep learning, the stars kind of aligned in a few ways. So the first thing was we had the internet for a long time, and people were sharing lots and lots of data on the internet. So there was a lot of available data. It was labeled however it was labeled, but it was there. And then on the other hand, we had this massive kind of computing explosion where all these GPUs were becoming far more accessible, much cheaper, much faster. And so with these two things together allowed us to really tackle some of these big data problems with the new compute that was available to us and with the data that was kind of just there. When we move to robotics and when we want robots in our environments doing things and we want to learn from that, I think what we might not have as readily accessible is that data component of it, because every piece of hardware is different. And we can try and push in the direction of fully generalizable models, but I think without coverage, it stops becoming an interpolation problem, becomes an extrapolation problem. And I think famously deep learning doesn't do so well. So once you're out of distribution, kind of all bets are off. So I don't know that we can use the same, we can hope for the same alignment of stars that happened for deep learning to happen again for robot learning.
But like we also have these transfer learning methods, which is complementary to that, right? So you still think there's a limitation to how much you can transfer, what type of skills and models you can transfer, right? Anyone else has a different opinion on stage? Everyone agrees? Okay.
Yeah. If I can add that briefly. Yeah, actually, then, considering deep learning stories, of course, the huge size of data is drastically changes performance in large language models. But then, as I mentioned, the case of the robotics is very hard to collect such size of the data. And considering the large language model, it's, from the viewpoint of human development process, is very strange. So the complete novice is trained with a very basic language, and at the same time, so knowledge of the law or the medical was very complex language. At the same time, every data is given, and GPU, and waiting 3 months, and suddenly the intelligence comes. So I think in the case of robotics, it's possible. We need to consider what types of skills and firstly obtained should be obtained. What is the foundation, in the sense of the foundation to obtain the most complex skills. And so now, again, some development of robotics researchers, so that I think that such kind of process is more and more carefully designed, what kind of skills is acquired gradually.
Great, thanks. Right, so we have the third poll here. So which of the recent advances that you have heard about or like you're excited about that's coming up from the learning space that you think that has very large potential to basically push mobile manipulation forward? Address some of the limitations that maybe that we have heard in the various talks in this sessions.
I don't know what are the big. I don't know what.
You had the limitations.
Advances, you know? LLMs.
So maybe some of the robotics, especially walking, regular robot, reinforcement learning shows quite good advantage, I think. So like an ATH animal, so this needs to buy the robot. That one is very impressive. So all training and simulations. And then reinforcement learning, collect big data, and directly translated the hardware and show big performances. But the case of the manipulation, the big difference is that in the case of the walking robots, it's okay in modeling the robot itself. Environment in their training, environment is a very, how can I say, hard condition for the robot itself. So it never appeared in the real world. But in such a case, the robot can walk and train in the reinforcement learning, then it can be directly adapted to the robot. But the case of the manipulation, our target is not only the robot, but also the object. And so such an tower closes, and today I show the scrum breaks. That is very hard to the simulation in the computing. So impossible to know everything in the simulation, I think. So yes, some of them are of course very useful, but then some of them very limited for the manipulation task.
Yeah, I think, I mean, it's not a recent development, but imitation learning is maybe for me the most powerful thing what can help us to make serious, scalable, transferable advancement in the area, in particular of manipulation. LLMs we are benefiting in robotics also from LLMs these days. I mean, maybe in a few days we'll not have any symbolic planners, what we learned about in the last half century because LLMs can generate such a symbolic plan in a faster way, and yeah, reinforcement learning invoking actually, yeah, what Tetsuya mentioned.
Yeah, I would also put imitation learning high in the list. LLMs, yes, I think there is a tremendous capability, but we need to understand how to ground things, which is a very important, big problem in my opinion. And I will also put the diffusion learning high up in the list. I think there are some very interesting ideas there.
Yeah, I totally agree. I think for the symbolic planning component of it, I think the grounding element is still going to be elusive. That's not going to be solved with just language, because the physical world will be what the physical world is no matter what you say about it. So being able to actually feed that back into whatever representation you have, because you know for a fact that something happened, is not something that's currently available. You learn a model and then that's just the way that it is. You cannot kind of keep fixing it based on your actual experience, your live experience. And the diffusion models I'm also quite excited about, because I think for a long time we've had probabilistic robotics and we've kind of followed the Bayesian reasoning, which I think is still good, but we kind of associated Bayesian to mean Gaussian. And that's kind of left us a bit stuck in the kinds of ways that we can model uncertainty with just these unimodal distributions. So I feel like diffusion models are going to give us a new way of representing uncertainties and representing the possibilities that roll out in terms of these long horizon plans. So I'm kind of excited to see what people are going to do with it in that direction.
I think that kind of sums up. So far it looks like the foundation models, diffusion models, LLMs, VLMs, also VLAs, there, human demonstrations. I think pretty much sums up what we have and what people think as well. So we still have some time for active questions. If you would still like to, if the audience would like to ask their own questions, you can still enter them. Let's see. We have one question. Maybe let's go with, what is the role of generative AI in robotics, and how do you predict its scalability in the real world? I mean, I think on the scalability is getting there with just the LLMs, right? And also, we've seen it with our vision language models in terms of even with videos, with Sora and things like that. So how do you see in terms of robotics that this would scale to real world applications beyond data sets? And you have any thoughts on that?
I'll look at it from the perspective of diffusion models with generative as a generative model. So what I was mentioning before about being able to predict the outcomes of actions, usually if you try to grasp something, you either successfully grasp it or you don't. There's not really an in-between. And if you wanted to model the world with Gaussians, which is what we're used to doing, it's very hard to have these two kind of binary outcomes being correctly modeled that way. Whereas if you were to be able to sample the potential outcomes via, for example, a generative model like a diffusion model, I think you would end up with a much stronger, a much more powerful predictive model compared to what we currently have available to us. So that's one place where I think generative models can be directly included into the way that we currently do our planning. As far as LLMs go and VLMs and LLMs and all the other acronyms that come out there, I see them as being really excellent translators between how robots understand things and how humans understand things. And right now, without them, you need to be able to code in order to make a robot do something. Now that we have language as that common, as now being a common thing between the two parties, it makes things so much easier and much more accessible.
I totally agree with this comment.
I think I totally agree too. So I guess this question was there before, but we didn't get to it last time. So humanoids, I think we've seen in the last year from the spike from the industry, I think we went from quadrupeds to humanoids. How do you see this going forward in terms of real world applications beyond research? So is this promising? Are we going to get there as how far we have got there with quadrupeds to industrial applications, or what are your thoughts on this? Maybe you tell me, let's start, because the last talk was about humanoids.
Yeah, I mean, it's a great time for humanoids, right? Because everybody is building humanoids. I'm happy to see so many platforms, yeah? So it's not easy really to build robots, believe me. But I'm a little bit worried actually, because again, people making a lot of promises. And I think what people, the expectations are very high, in particular in combination with large language models and foundation models and so on. But many people are actually, they don't really understand the problem.
What it takes.
Yeah, and therefore we have to be a little bit careful, because otherwise we will fall very, very deep, Not, I mean, everybody, all these big whatever YX people building humanoids. Yeah, but I think this is the technology is needed, and this would be a solution for many problems actually in private environments, in care, in manufacturing. I mean, building system with the versatility of humans, this would be fantastic. Yeah, and the problems are not really solved by building the mechanics. We have to build the entire thing, the mechanics combine the body and the brain and the mind in order to achieve this, to meet some of these expectations, what you see in videos, what are posted these days on the web, Yeah, but it's an exciting area of research, so I recommend it to everybody. Start doing research on humanoids. Yeah, there are many problems, and I think the problems is really how to connect the physics of a humanoid with high number of degrees of freedom, not only the motion planning actually, but also the physics of a humanoid to whatever LLMs, to all these recent developments and advancements in AI. And how to get from 20x to 1x, this one of the problems actually, but it's not only related to humanoids, it's related to robotics in general, I mean, we as roboticists, we have to render our videos in a faster way so that they move in a human-like way, but this is not actually what it should be about, yeah.
So actually, so I said, Waseda developed the first humanoid 50 years ago. At that time, there's not such kind of discussion. No one believes that it's a useful one. Okay. So now it's very interesting. Everyone now started to discuss it could be useful. So actually, we often discuss about for replacing the human's work. Human shape is useful. Such kinds of explanation often happened. But interesting. So recently, we can see the many mobile robots in many areas for guard or mobility or something. If it could be one arms artist in the future, I think. And 2 arms, maybe, of course, 3 arms, 4 arms could be acceptable, but some of the work tasks could be done in the human-like robots. We cannot say it's a humanoid robot, but the shape could be close to the human-like machines. And if we'd like to then ask the robot to then work instead of us, that is one of the stories with an advanced intelligence and deep learning or something like this. I'm not sure the humanoid 2 legs, 5 fingers, that is very hard, I think. But yeah, some of the shapes could become similar to us.
Mm-hmm. Great, thanks. I think we have time for one more question. What is stopping us from getting these robots to our homes? I guess the first part is going from 20x to 1x. It's on the board itself.
Speed is the first one. Okay, you wanna? Okay, this way. Speed, safety, costs.
Safety, I think, is big on the list. and we are not paying enough attention to safety. I mean, cost. Absolutely, absolutely, absolutely. I mean, we really don't have a killer application for a robot at home except the Roomba. If you think about it, the only robot that has made it to households is the Roomba, I think.
I guess the mobile manipulator, the cheapest one is like the Hello robot, right? With their arm.
The stretch.
Yeah, the
right?
stretch.
The stretch.
Yeah.
It's still 25K.
25K.
And if you get the fancy grippers and a few cameras, I think it's around 30K.
And how long does it work?
Well, I think it's a very reliable robot, actually.
All right, let's thank the panelists. We are right about time. And we can move on, I guess, to closing remarks and awards. Daniel? Maybe you should, if you have participated in the poster or the talks, please wait because we still are going to announce the awards and yeah, a few closing words.
And if you haven't published, it's also interesting to, to see
Still
who
wait
won.
to know who won.
Trying to. No. Trying, but. Yeah, probably. Only one. Only this one. We only have only this one, so. Okay. Let's try the other board just in case. They're the same. Okay.
Okay, before we close, a brief introduction of our one of our sponsors, Ubitech, from Dr. Xanthi Papageorgiou.
Hello, I'm Xanthi Papageorgiou. I'm the head of the Robotics and Cognitive System Unit of Ubitech. Ubitech is a highly innovative software house, system integrator, and technology provider established in Athens back back in 2005, Athens in Greece, concentrated initially in the Greek, Balkan, and European market, acquiring several European Commission grants for sophisticated R&D initiatives, extending currently our operations with the international activities, though our subsidiaries and offices in Cyprus, Belgium, and Argentina. Ubit is established to provide leading-edge ubiquitous security technologies, intelligent technical solutions, consulting services to businesses, organizations, and government. Our motto is efficient and effective secure access to any service, data, and information anytime, anywhere, and our vision from e-everything to you-everything towards the creation of highly innovative, intelligent, ubiquitous network micro-societies. Our main business activities are related to European and national co-funding research programs, system integration and custom software development, as well as e-services and e-processes, and technology provision and IT consulting. Our technological expertise and R&D competencies are related to computing systems, software and services, autonomous networks, IoT and network softwareization, data science and intelligent computing, knowledge and social technologies, digital security and trusted computing, agri-food technologies, and of course, intelligent robotics, control and automation. In these aspects, we have expertise in autonomous robotic systems like multi-agent, aerial, mobile, underground and underwater robotics, autonomous robot control and decision system, intelligent robot control, all kinds of mobile robotics, autonomous mobile manipulators and vehicles navigation and task planning, of course, multimodal sensory data processing, machine learning and mobile sensor networks and robot perception, and on the top of all of them, human-robot interaction. Our application domains and vertical industries are related to healthcare, industry 4.0, telecom, energy, transport, agri-food, maritime, aviation, safety and security, and insurance and finance. Right now, Ubitech has a track record of more than 150 co-funding research programs and large-scale information technology projects. Ubitech ranks first among all Greek for-profit organizations in terms of European Commission grants acquired for the whole European Union Horizon 2020 funding program. And we have a research partner network in a large industry, RTD performing SMEs, research institutes and universities, and some of the ongoing robotic projects right now are regarding advanced AI robotics for autonomous task performance. In another part, smart autonomous robotic deliveries for small logistics, and search and rescue activities for emerging technologies for the early location of entrapped victims under collapsed structures, and advanced wearable for risk assessment and first responder safety in SAR operations. Also, we have some projects for safe and trusted human-centric artificial intelligence in future manufacturing lines. Here, we have the honor to sponsor the Best Poster Award in order to support this very good initiative towards this mobile manipulation and embodied intelligence. And I think now I'm in a position to announce the winner for the Best Poster Award. The winner is the Mosaic, a modular system for assistive and interactive cooking.
Wait.
Want
to announce it?
It's up to you.
All right. Have the best paper award that is going to Spot Compose, a framework for open vocabulary. All right. It's a very long title. Congratulations. Congratulations. Yeah, let's go. All right, and with this, we conclude our workshop. I hope you enjoyed, and now we can go to the welcome reception. Do you know what room it is? Exhibition hall. All right, we come out and we come inside again to the next door. I hope you enjoyed and enjoy the rest of the conference. Bye.